performance is double 2. In the figure, we can see that the number of transistors shown as the original triangles indeed keeps increasing during the past 48 years. At the time before 2005, as most CPU is composed of a single core, with the number of transistors keeps increasing, the performance of a single thread is increasing too. However, due to the power consuming and the temperature limitations, CPU began to use multi-core architecture nowadays. Though the number of transistors keeps increasing, the performance of a single thread remains unchanged and results in some typical technical trends. The first is that the number of cores keeps increasing. In some commercial CPU, such as Intel and AMD products, the maximum number of physical cores have increased to 64, which is almost double in the past decade. The second is that the memory capacity of each core is decreasing. And so is that the bandwidth of the memory and the network per float. They are decreasing with more cores in a CPU. So with the number of cores in CPU keeps increasing, the memory capacity and the memory network bandwidth is not increasing so fast as the number of CPU cores. So for our HPC users, now the main challenge becomes how to release the full power of CPU under such a new trend with multi-core architecture. To release the full power of CPU, we need the performing tools and a new optimization methodology for large-scale parallel computing. In the performing tool part, our department have developed a new software called TI. This tool combines all the functions of current performing tools in Linux platform, such as the perf, top, IOState, and other software. TI can be used for monitoring all the performance characteristics of HPC clusters. It divides the performance results into 4 categories. The first is a fine-grade CPU or GPU, a fine-grade CPU or GPU microarchitecture result, including the usage ratio information, the G-flop speed of different instruction sites, and some other information such as the number of cycles, instructions, and the CPI. The second is the data throughout from CPU or GPU, including the reading and writing bandwidth of cache, memory, PCIe, and NVLink devices. The third category is the network bandwidth result, including the high-speed communication network, such as InfiniBand or OmniPath network. It also can monitor the Ethernet bandwidth and the message side of each package. The last part is the I/O data throughout result, including the I/O bandwidth of local disk devices and the NFS service. In addition to the performance analysis tools, it is also necessary to ensure that the cluster system is at the best performance before running any HPC applications. In the HPC system, the parameters of multiple systems need to be adjusted to ensure the best performance. For example, the BIOS, the system kernel, and some system service, the compiler options, and the communication libraries. All these parameters should be carefully tuned for different HPC applications. When we are verifying the cluster performance, we use a variety of performance models, including the roofline model, as shown in the left, and the communication matrix. These 2 models, we can check the memory bandwidth, the computing speed, and the network bandwidth and the latency. After the introduction of performance tool and the system configuration, now let's talk about the performance issue for large-scale parallel computing. Here we take the CFD software OpenFOAM as an example. The left 4 figure, we can see that shows the monitor results from TI when running a test case in OpenFOAM. From these 4 figures, we can see the performance information about the CPU usage, the G-flop speed, the memory and the network bandwidth. By analyzing the performance result, we can have a detailed understanding of the status of all the devices in the computer node. From the left top figure, we can see that the CPU usage is very high, but the flow speed in the right figure is relatively low, though very small amount of AVX instruction is used for the computation. The memory bandwidth has almost reached the upper limit of the current platform. The network bandwidth is moderate, and some spikes appear during the output process. Therefore, combining this result, we can conclude that the memory bandwidth is the main bottleneck for OpenFOAM running on current platform. However, these are the characteristics of a small-scale parallel computing test case, where we only use 4 computer nodes. When the computer node number continues to expand, for example, when we use 40 or 100 computer nodes, the total memory bandwidth of all computer nodes is increasing. Gradually, the memory bandwidth limitation will be reduced. However, the communication capacity and the I/O load will gradually increase. Therefore, in the case of large-scale parallel computing, the performance issue will change from the memory bandwidth to MPI communication or I/O limitation. This is also what we emphasize in HPC parallel computing, that the larger is different. So why does the performance issue change from small scale to large scale in parallel computing? To explain this question, we have to go deep into the perspective of HPC architecture. The left figure shows a typical architecture of a modern commercial cluster. The above figure draws a diagram of a single node composition. In a single CPU core, there are L1 cache, L2 caches, and the operation units. And a single socket includes multiple cores and their attached L3 caches, as well as the memory. Normally, there are 2 sockets in a computer node, and they are connected by interconnection devices, such as QPI or UPI on inter-platform. The below figure shows a typical cluster. As we can see, multiple computer nodes are connected through a high-speed data network, such as InfiniBand or a mini-path. And the computing data is stored in the parallel storage system. All of the units in the left figure compose a modern cluster system. So when the cluster is running with an HPC application, in the view of CPU, the data could come from different devices. The available data capacity and the latency are quite different. The CPU caches are the fastest devices, and the latency is less than 40 cycles, but the capacity also the smallest. The second fastest device is the local memory. The latency about 10 times than that of the caches. When communicating with other computer nodes with RDMA technology, the data may transfer through the InfiniBand or other high-speed network, and the delay is about 25 times. The local storage and the parallel storage system are the slowest. When reading data from these slow devices, the latency will cause the CPU to stall, resulting in a significant decrease in the computing performance. In the large-scale parallel computing, because more data is transferred from the network, so the network communication is very easy to become the main performance issue. Based on above discussions, we propose a new optimization method for large-scale parallel computing. According to the latency of different devices, in the precise performance optimization, the first step should be the optimization of the I/O performance. I/O precise, including the parallel field system and the field format. The next step is to optimize the network communication, including changing the MPI functions and optimize the load balancing. The third step is the optimization for memory size, including balance the reading and writing data size and use shared memory. Finally, we optimize for CPU computation, such as vectorization and cache usage. In the third part, we will demonstrate the application of the new optimization method in some real HPC applications. We have tested with many HPC applications, and we group them into two categories, including the weather and the ocean models and the material science models. In the first part, we will have a look at some weather and ocean models, including NEMO, WRF, GRIPS, and MUM6. First, let me give some introduction about these models and the test case we use. NEMO is a state-of-art modeling framework for researcher activities and forecasting service in ocean and climate service. This software is developed in a substantious way by European researchers. We use the Indian Ocean test case of NEMO to simulate for 10 days. In this test, the computing load is very large. It includes more than 4 million horizontal grid and 75 vertical grid. The total number of unknowns is more than 1 billion. The number runs for 7,200 steps, and the time step is 120 seconds. The second is a famous weather research and forecast model, WRF. The WRF model is the next generation microscale multiple weather prediction system. It's designed for both atmosphere research and operational forecasting applications. In this test, we use WRF to simulate the weather process of Domain 1 and Domain 2 in East China. We can see these two figures we can see these two domains in this figure. The number of horizontal grids in these two tests are more than 1 million and 4 million. The number of vertical grid is 81. The WRF includes multiple physical models, and we can find the setting of each physical model are listed here. The third model is GRIPS. It is a multiple prediction system developed by China Meteorological Administration. The GRIPS model includes two submodels, the global forecasting system and the micro-scale prediction system, which is used for the global and regional multiple prediction respectively. We use two test cases to test the GRIPS model. The first is a global simulation with different resolution cases. The second test case is a microscale problem. It simulates the atmosphere condition of China mainland for 24 hours. The last model is MUM6. It's a multiple representation of the ocean dynamic process. This model can couple with sea ice or other multiple models to simulate the global ocean dynamic process, including the north and south poles. In this test, we use the OM4 global test case, where the horizontal resolution is 0.1 degree, which is almost the highest resolution in current global ocean modeling. The simulation runs for 6 months, and the time step is 360 seconds. Based on the multi-layer data size optimization method, we use 4 steps to optimize this weather and the ocean applications, including the I/O, the network, memory, and the CPU parts. In the 4 boxes, we have summarized all the operation in each step. In the following part, we will give more detailed descriptions. First, let us see the I/O optimization. In the NEMO model, it can use the XIOS server for I/O operations. We could adjust these parameters and let it use more memory buffer to improve the I/O performance. From this operation, we can have 3% performance increasement with a parallel system. In the WRF model, it can use multiple high-performance I/O software packages, including the basic NetCDF software, which is the default field format, The PyroNet CDF and the PyroIO libraries, with these libraries, a large number of processes can output the results viewed separately. The IO software can also perform the PyroIO process. We have implemented each package separately, and the improvements are listed in this figure. And we can see that with all the IO software package, the run speed has increased from 3 to 4 times with different numbers of CPUs. We may have heard of the Lustre field system can provide high performance in IO process. This is because the Lustre field system have the ability to strip the data over multiple OST storages. The strip count can be set on a field system dictionary or field level. In the GRIPS test case, we show the usage of stripping field with Lustre field system. For the GRIP software, it does not support to use some high performance IO software. So we use some hardware optimization method based on the Lustre field system. The IO field in GRIPS can be divided into 2 parts. That is the blue and the red ones. The first part is the log fields, which has a small size but a large number. The second is the input and output field, which has a large size but a small number. When we use more than 8,000 cores to compute GRIPS, the IO process only consume 4.6% of the runtime. However, when we double the scale to 16,000 cores, the IO time is also doubled to 9.7%. This can cause a huge side effect on the scalability of GRIPS. In order to optimize the IO process, we use 2 optimization methods. We use 2 optimization methods based on the Lustre field system. First, we put the log field into the MDT storage, which is typically configured as a high IOPS and optimized for small IO date. Secondly, we put the large input and output fields into the OST storage and configure these field strippings to store data over multiple OST storages. After this optimization, the run speed of GRIPS has increased from 1.27 to 1.67 times over 8,000 and 18,000 cores. The second optimization step is related with the network. As we know, there are mainly 3 kinds of network topography, such as Torus, Dragonfly, and Factory. For parallel computing, most HPC software use MPI library. In each MPI function, there are many different algorithms. For example, we can see in the right in this figure, the reduce function could use send receive or theoretical algorithm. For each MPI function, different algorithms may have different performance on a specific network topography. So in network optimization, we use the entire MPI software and adjust the algorithm parameter for the best performance. When running emo application with 16,000 cores, the MPI function takes more than 50% of the time. The hotspot function is the MPI receive and the MPI or reduce function. However, as MPI receive is a very simple function, we can only adjust the parameter of the or reduce algorithm, and the performance has been improved about 2.9%. In the GRIPS application, the most consuming MPI function are send and or reduce functions. It is similar that when we adjust the or reduce algorithm, and we have achieved 1.30% improvement with 4,080 cores. However, when the parallel scale is doubled to 8,160 cores, the improvement ratio has increased to 11.7%, which is a significant improvement. In month 6, the in MAP6, the computing domain is decomposed in the horizontal grid along the X and Y direction. Each subdomain is assigned to a PSICE, and each PSICE are assigned to a physical thread. Finally, one physical thread is responsible for a computation of one subdomain. By default, the subdomain of the PSICE are bound to the crossing order. In the computation PSICE, there will be a lot of communication between the adjacent regions, as we show in the black. However, due to the difference between the hardware topography and the subdomain decomposition, this communication may occur between computer nodes, resulting in exhaustive computing network bandwidth and becoming the more bottleneck during the computation. So a better computation model is to adjust the precise binding order into a two-dimensional format, such as the colored box as shown in the middle figure. At this time, the precise in the box is bound to the core in a single computer node, which can greatly reduce the amount of data communicated between the internode and the internode. In order to analyze the amount of communication data size, we can calculate the total amount of internode and internal data size by these two formulas. If we define Tx and Ty as the number of grid points in X and Y directions, and Nx, Ny, and Ps, Py as a number of computer nodes and the PSICEs used in X and Y device directions. And the K0 is a constant number of communication message size of each grid point. Then the total amount of internal communication message is F1 and given by the first formula. And the total amount of internal communication message size is F2 and given by the second formula. To find the best performance of Nx, Ny, and the Ps, Py, we can use the following table. In this table, all the possible parameters of Nx, Ny, and Ps, Py are listed, and the corresponding result of F1 and F2 are shown in the table. Finally, the best parameters for precise binding can be obtained, which has the smallest amount of communication message size in both the inter and internal communication. In Wolf software, besides the MPI parameter organization, you could also use a hybrid parallel model with MPI plus OpenMP. When we use the pure MPI parallel model, the communication is very complex at the large scale parallel computing because each processor had to communicate with other processors. However, when we increase the thread number in each PSICE, we can decrease the PSICE number, and the communication capacity is also reduced. In the right table above, we can see that the best number of the thread keeps increasing when we use more CPU cores. After all the optimization, we have increased the speed up ratios of case 1 for 2 times. In the case 2, with larger mesh size, the parallel scalability is much better. In the CPU part, to improve the performance, we directly implement the AVX 512 instruction side to improve the vectorization. In the Greek model, the main computing PSI is a Helmholtz equation. In the computational loop, the three-dimensional stencil computation form is implemented for each grid point. Because the location of this data are not continuous in memory, the compiler could not automatically use AVX or AVX 512 instruction side to achieve the vectorization. We can directly replace this stencil computation with AVX instruction side and overlap the data side with computation PSICE. Finally, the CPU computation performance could be improved by 1.8 times. The second part, hello?
There is a question in the chat whether in your MLDA methodology, you have a single pass optimization for IO, network, memory, and CPU. The question is also whether you have considered an outer optimization loop, for example, in case something changes like an upgrade to CPU or network capacity.
Sorry, I didn't hear clearly. Can you repeat?
If you want, you can also read it in the chat if you have access to that. So the question was, you have this inner loop optimization to optimize your algorithm with respect to IO, network, memory, and other resources. The question was, is there also an outer loop for optimizing in case of changes, for example, if there's an upgrade to the CPU?
Okay, let me find where. Okay, let me first stop the loop and then let me see.
I mean, if you can't answer the question now, then maybe just finish your presentation first.
Okay, let me first let me continue. Okay, after the presentation, I will answer all the questions. Oh, sorry. Okay, the last part is applying the optimization method in some material science application. The first is the VASP software, which is used for electronic structure calculation and quantum mechanic and molecular dynamic simulation. In this test, we simulate a crystal structure system with a different number of atoms. The second is the GROMAX application, which is a versatile package for perform molecular dynamics. The test case a pair of traumatis. The number of atoms is nearly 3 million, including protein, liquid, water, and ions. The third software is CP2K, quantum chemistry and the solid state physical software package. The test case is a benchmark from CP2K website. It's a lithium hybrid crystal with 260 atoms and 432 electronics. In the material science software, there's not much IO data or large input-output fields. So our optimization methods are reduced to 3 steps. That is a network, memory, and the computations. First, let's see the optimization method for VASP. In network, we adjust the MPI parameter of the MPI bcast and the reduce function. We also use some more compacted storage formats such as less 2D block cycle format, which can reduce network communication and also reduce memory bandwidth. In the CPU optimization, we compile the software with a high vectorized instruction set to increase the flow speed. And we also made some algorithm optimization to reduce the amount of computation. The algorithm of optimization is achieved by an efficient 2-step tri-diagonal form transformation of the matrix. The algorithm optimization could speed up the application from 1.7 to 3.35 times. After all the optimization, the parallel scalability of VASP software can reach 10,000 cores, and the speed up ratio could could remains increasing. For GROMASS and CPU2K, we have had the same optimization steps. In the CPU optimization, we also use some high performance mass library, such as FFTW and MKL library. To show the optimization result, we have compared the performance of the same task case in GROMASS and CPU2K with the other supercomputing platform. It could be seen that all reduce are almost the fastest among all the platform. Okay, that's all over my presentation. Thank you, everyone. Let me find the questions. Is there questions? Okay.
Hello.
Yeah.
Thank you, Longxiang, for your great presentation. I can ask. So in your presentation, you mentioned that the scaling. So when the scaling is scaled up, I mean when the system scale up and the performance distribution and performance bottleneck becomes different, right? You know, like what are the main factors that cause this situation?
Okay, let me go to the page.
Yeah,
okay.
earlier.
Yeah. I think maybe maybe this pages can describe it more clearly. When we use a small scale of the computer nodes, we can imagine that the more data are stored in the memory or the faster devices such as CPU caches or memory. But when we use a large amount of the computer nodes, more data should be transferred by the network. And so this may cause more CPU stores than the small scale computing. That's why the performance issue may change between the small scale and the large scale parallel computing. And this is as we show in this figure. When we calculate the open form with 4 computer nodes, the main bottleneck may be the memory bandwidth. But when we use more than 100 or more larger computer nodes, more data are transferred by the network. So the network bandwidth may be increased. And the total memory bandwidth is also increased. So the memory bandwidth limitation will be reduced, and the network bandwidth will be the main bottleneck.
Okay, so in this case, can we just have some elastic, like from elastic like a network configuration? Would that solve that problem as well?
I think we can't change we can't change the how to say that we can only reduce the limitation. In order to reduce the limitation of the network, we can use some methods such as changing the communication library, and let me use this slide. I think yeah, we can change the how to say that, we can change the algorithm of the MPI functions, such as we can change it from the send receive to the hierarchical algorithm. This could improve the performance in the factory topography. And we also could use some other methods such as the precise binding. We can change the binding format from one-dimensional to two-dimensional. This will reduce the communication amount of the between the different computer nodes. It will also increase the performance. And I think this is a two main method to improve to reduce the network limitations. And maybe okay.
Thank you very much for the explanation.
So just to clarify the question in chat, I like the 4 steps of your methodology, but I want to know, is there a step 5 where you go back and revisit the other ones if you've changed the CPU, for example?
Okay. Right now, we just following these steps to optimize the Hpc applications. But it's really true that when we optimize the such as when we optimize the memory bandwidth, the network performance may be changed. So now we are still working on how to improve the optimization methodologies, and it's really I think a shortcoming of our method. This is really a shortcoming of our method. It really is, I think it is a good question, and we were working on it.
Yeah, thank you for that. Nice talk. Bye.
Yeah. Okay. Thank you, everyone.
Any further questions? That does not seem to be the case. So then let's thank our keynote speaker again.
Steffen, there is one more question by Connie.
Yeah, okay. So it just came in. Is the optimization automatic or manual?
The optimization is all the optimization performed by manual. Right now we did. Right now we're still working to. We are working on how to make this optimization method automatically with our TI software. But as you see, the optimization for different applications are quite different. So right now we didn't see any possibility to achieve automatically optimization of HPC applications. So we have to find so we have to perform different HPC applications with different methods.
Okay, thank you. Now I wait 1 more minute whether there's another question. Okay, so at least now I don't see any further question in the chat nor in Zoom. So then let's thank our speaker and we enter a break of 10 minutes and the session continues at 3:15 Central European time.
Okay, thank you.
Thank you so much.
Thank you.
Who is the session chair for the next session?
Yiming Tang, I see already in Zoom. Could you?
Yeah, I'm here.
Great. Could you check with the speakers of the next session that everyone is here and the plan goes? So
okay.
in 10 minutes, you can start the session. Great. Yiming, are you in the Slack channel?
Yes,
Great.
I'm in the Slack channel. Just for checking, is Nupia submit here or not? And is Mohammed Mazaja Sotai here or not?
Hi.
Hi, welcome. We are waiting for the starting of the session, and I'm just checking the presenters available here.
I think maybe prepare to play the video in case someone didn't show up or late, I think.
Okay. So you mean I post the YouTube link here or some others?
There's a I think a YouTube playlist for each channel, right? So we can, I think it's somewhere.
Okay.
It looks like all the presenters are here now, right?
Yes.
Okay, cool.
So I don't think we need to have a fallback plan. I think it looks okay. We're gonna wait for 4 more minutes and then we can start, I think.
Yeah.
Okay.
Just like
A chance to stretch the legs a little bit and then we can come back.
I think it's the time to start the session. Okay. First, I'd like to welcome everyone to join the live session of hardware performance. I'm the session chair. My name is Yimin Tang. I'm the postdoctoral fellow from the Concordia University in Montreal, Canada. Today we have 4 papers here. The live session will take 1 hour. For each paper, it has 10 minutes for the presentation plus 5 minutes for the questions. If you have any questions, you can have 2 ways to propose your questions. First, you can raise your hand in the Zoom and ask the questions direct to the presenters. Second, you can put your questions on the Slack channel and I will help you repeat them and the presenters will answer your questions in the Zoom. Due to the time limitations, some questions may not be answered in the live session. I encourage the presenters to answer the questions after the live session. Now, let's welcome the first presenter, Sophia Chattoyi from the Brown University.
Hello?
Yeah, I can hear you.
Okay, sounds good. Hi, so my name is Sophia Chattoyi. I'm a 5th-year PhD candidate at Brown University. And today I will be presenting about the alternating blind identification of power sources for mobile SoCs. So we will start with the introduction, then we're gonna get to the problem formulation. Then I will introduce the alternating BPI. Afterwards, I'm gonna show you the results. And if you have enough time, we'll discuss the related work. And then we're gonna get to the summary. So basically the need for faster system on chip has accelerated scaling trends, which enabled new applications that require intensive computation, leading to a considerable power density increase and raising critical power and thermal challenges. So as you can see in figure 1, the power density actually exponentially increases with the technology node. So the ability basically to measure power consumption at the fine granularity or at the hardware unit level is essential for the operation and improvement of mobile SoCs. For instance, this could be used for power and thermal runtime management. However, mobile SoCs, they lack the ability to sense the power at the hardware unit level because of the power and area overhead that current sensors incur. However, on the other hand, mobile SoCs are usually enabled with embedded thermal sensors to measure the temperature at the hardware unit level. And there is usually like at least one thermal sensor per hardware unit. For instance, in figure 2, I'm showing a CPU ARM big little architecture with 8 cores. Usually, like in the best case, you would find like 2 power sensors for the whole cluster. However, you would find at least 8 thermal sensors, like where you would find like at least 1 thermal sensor per core. So actually the idea in here of this work is that using thermal sensors to measure the power at the hardware unit level is a good way to enable fine-grained power sensing without any extra overhead. And actually the relationship between power and temperature actually is described by the heat diffusion equation, which is shown on the top right of the slide in here. So the heat diffusion like takes into consideration many factors, including like the conductivity of the material, its density, and so on. So actually, if we perform a spatial and temporal discretization of the heat diffusion, we're gonna end up with the following state space model, where temperature at time k is a function of temperature at time k minus 1 and the power at time k. And the A and B matrices in here are modeling matrices that depend on our circuit. So the A matrix is a thermal conductance matrix, which represents the natural response, like in the absence of power, basically. So it could describe, for instance, the cooling process of like the processor or the circuit. And then the B matrix represents the forced response matrix, which is composed of both thermal capacitance and thermal conductance. So basically, and then the TK in here and PKs are the vectors that denote the temperature or the power SoC hardware units. So the TK, let's say like if you have like 4 units, then the TK would be a 4x1 vector. Each value is gonna represent like the temperature of each one of the hardware units. And the same for PK. Each one of the values would represent the power of each one of the hardware units. So the problem in here is that, so if we are able to estimate or compute the A and B matrices, then actually we could use the temperature just to estimate the power values of each one of the hardware units. So the proposed work in here, the alternative BPI is composed of 2 steps. Like we have an off-learning step where you estimate the A and B matrices using the state space model in here. And then in runtime, we use the per unit as shown in here. So we use the per unit temperature sensors and the total power consumption to estimate the power per core, basically. So the inputs are the total power and temperature per core. So first of all, to estimate the A matrix, we use, which is like the natural response matrix, we use the transient temperature traces, basically in the absence of any power. So like if you stress the different cores and then like we kill basically the different workloads and turn off the hardware or the different blocks, the state space model becomes as follows. Because pk equals 0, it becomes tk equals atk minus 1. And for reference in here, I'm showing how the transient traces look like. So on the y-axis, we have the average associated temperature, and you could see like the cooling process. So in here, as shown, so I'm showing on the right side the algorithm for the alternating BPI. So to estimate the A matrix in here, we use a least square minimization, where we try to minimize this term in here under the constraint that the values of A should be positive because it represents thermal conductance. And then basically after estimating the A matrix, we try to estimate the B matrix, which is like the hardest to estimate. So we start first of all by making an initial guess about the B matrix. And then in the next slides, I'm going to show you that we're going to be like alternating between two steps, the P step and the B step, to make better estimation of the B matrix. So to make an initial guess about the B matrix in here, like we derive like the expression of the initialization value like from the steady state, where the temperature at time k equals the temperature at time k minus 1. So the state space model becomes as follows, like Ts equals A times ATS plus B times PS. And then actually we could derive like the following equation 5, where Ts equals the R matrix, which is the power transfer matrix, times PS. And from the physical characteristics of the R matrix, we could actually derive the following initialization for the B matrix. So we know that the power transfer matrix need to be a symmetric matrix with the highest values in the diagonal. And then basically we keep alternating between the P step and the B step. So in the P step, we try to estimate the P vector given an initial guess about the B matrix. And then in the B step, we try to estimate the B matrix given an estimation of the PK vector. And we keep repeating these steps for a certain number of times. So in the P step, basically in here, as shown on the right side, we solve the quadratic programming problem, which is derived from the state space model, where we try to minimize this term under the condition that the total power consumption should be equal to the total power that we have as input. So the number of unknowns in the P step is equal to the number of power sources times the number of time samples. And then in the B step, we use a least square minimization to find the B matrix given the previous estimation of the PK vector. So in here, the number of unknowns is just equal to the number of values in the B matrix, which is like the number of power sources square. And then in runtime, after estimating the A and B matrices, we could use actually the same step as the P step to estimate the power. But at this time, like we won't be changing the A and B matrices, they're gonna be now fixed. So in order to verify, the proposed work in here, we used hotspot, which is a thermal simulator that takes as input the total power, the per unit power consumption, and gives as output the per unit temperature. And also we give it as input the layout that we would like to estimate the temperature for. And then we give as input to the alternating BPI in here, as previously mentioned, the per unit temperature and the total power. And then the alternating BPI is supposed to estimate the per unit power, which we can compare to the per unit power that we gave as input to hotspot to verify the accuracy of the model. So we compared our work against 2 other blind identification techniques from the literature, using 3 different benchmarks. So we are using like a 4-unit layout, a 9-unit layout. So these 2 first benchmarks are homogeneous. So all the units are similar. And then we have a heterogeneous layout with 6 units, using like a big little GPU architecture. So as you can see in here, the alternating BPI, like as you can see, to begin with, like the power estimation error increases as the number of units increase and as we move also to the heterogeneous case. However, the alternating BPI not only was able to estimate the power with less error, but also it kept like a stable estimation error as the number of units increased and also as we move to the heterogeneous case. So this figure shows like the power estimation against one of the works that I presented earlier, the BPI assessed from the literature. So in blue is the actual values, the power values, and then BPI SS is in green, and then in red, the alternating BPI. And basically, as you can see, the alternating BPI is actually almost, estimating, the exact values for all the clusters with the same accuracy as opposed to the previous work. And then we use this work, we try to apply this on a commercial SoC. So basically, we use the Snapdragon 865 in here. I'm just gonna get to the results. If you have any questions about the setup later, I would be happy to help. And then yeah, so here's the slide. So basically, we try to characterize different mobile apps. We use like a CPU benchmark, GPU benchmark, VR, AI, and then augmented reality as well app. And then using the alternating BPI, we were able to estimate the power consumption of the different units. And that's what figure 7 is showing. And then figure 8 is showing the percentage power consumption of each one of the units. And there are a lot of insights in here. The main one that I would mention in here is that even with a new hardware units included in the state-of-the-art SoCs, like the CPU is still representing 60 to 75% of the power consumption, no matter the workload that you are running. So quickly in here, so there are different approaches for related work in the related work that try to estimate this.
Sorry to interrupt you. Sorry, the time is limited. Can you have a quick?
Yeah, I'm gonna summarize. Thank you.
Thank you.
Okay, so to summarize in here, so in this work, we proposed a new technique for blind amplification of power sources. The proposed approach decreased the estimation error to 1.9% as compared to 11%. And the accuracy of the proposed work was verified using simulation and validated using experimental data. Thank you.
Okay, thank you for the speakers. Is there any questions from the audience? Okay, I have a questions. I have a questions for the multiple sensors. I wonder if hardware unit have with multiple sensors, how do you deal with this case?
So you're asking like, how do you deal with a case where hardware unit does not have thermal sensors?
Yeah.
Well, this is a good question. I guess, this work, so there is a solution for this, but it's beyond this work, I would say. Usually people, they try to make, a sort of like interpolation, like thermal interpolation. So if you have like, let's say a certain location in between two sensors for which you want to measure the temperature, you would make a certain interpolation, and there are different techniques for this. And then after making the interpolation and making estimation about the temperature, you could use the same proposed technique in here to estimate the power.
Okay, thank you. Is there any other questions? Okay, let's thank the speakers again, and let's welcome the second presenter, Marcus Felton.
Okay. Okay, I think you can all hear me and see my slides.
Yeah.
So with that, welcome to my presentation. I'm Marcus Felton from the Center for Information Services and High Performance Computing at the Technische Universität Dresden. My colleagues and I investigated the memory performance of AMD EPYC Rome and Intel Cascade Lake SP server processors. And our motivation basically comes from an HPC standpoint. And in that market, x86 is still the dominant architecture. Of the current 500 systems in the top 500 list, some 480 something systems use x86. And in recent years, AMD's market share started to increase after many years of basically absence in that list, especially thanks to the rise of the AMD Zen 2 and Zen 3 architectures, as you can see in the right-hand picture. What came with the increasing number of cores in recent years is a increasingly complex general architecture and memory architecture in particular, which is relevant because many applications rely on data placement and memory access patterns for their performance. Especially when you consider that, especially the AMD architectures nowadays are mostly non-uniform memory architectures or NUMA architectures, meaning that the main memory cannot be accessed by all cores with the same latencies, and that depends on their position. And this can be shown when looking at the architectures in particular. So let's start with the AMD architecture. This is a multi-die approach that has been taken. AMD uses one central I/O die, and depending on the configuration, up to 8 so-called core complex dies or CCDs, which in turn are populated by 2 CCXs or core complexes, which in turn have 4 cores each. The Infinity Fabric is used to connect all the components, these is, CCDs, to the I/O die and to the I/O and memory interfaces. However, as you can see in that picture, there's no direct connection between CCDs, which we'll see later on in measurements as well. And just by looking at that picture, we can already guess that this is a NUMA architecture. So for instance, if you assume a memory access from a core in the top left corner, and that core accesses its memory in that top left corner, this latency will be lower compared to if that core tries to access memory in the bottom right corner, for instance. The AMD EPYC Rome processors can be shipped with up to 64 cores, and they use a modified Moesi coherence protocol. So we know at least that the cache lines can have the states modified, owned, exclusive, shared, and invalid. Some other states have been mentioned, but not properly defined by AMD, so we didn't analyze them. Intel uses a different approach for their Cascade Lake SPP processors. They use a monolithic design in which all components are aligned within a 2D mesh grid. The system is not by definition a NUMA system, but it can be configured to expose 2 NUMA nodes to the operating system via the subNUMA cluster setting. These processors come with up to 28 cores and use the massive coherence protocol, so cache lines can be in states modified, exclusive, shared, invalid, and forwarded. So let's take a look at the test systems and benchmarks we used. We used obviously 2 different test systems. One was our own HPC cluster with AMD EPYC Rome nodes with 2 × 64 cores and a nominal speed of 2 gigahertz. These nodes are populated with the fastest memory you can use with these processors running at 1600 megahertz. And the Intel system we used we got access to that from the Erlangen National High Performance Computing Center. And these nodes were populated with 2 × 20 cores and running at 2.5 gigahertz and memory speed of 1467 megahertz, which is the fastest memory speed you can use with these. Because both systems were provided by different entities, they run different operating systems. We couldn't do anything about that. And both systems were used to expose NUMA nodes to the operating system. So in the case of the AMD system, 4 NUMA nodes per socket were exposed to the OS, and 2 NUMA nodes per socket were exposed by the Intel system. The benchmarks we used were in-house developed by us. We used the Benchit benchmarking framework and the x86 membench benchmark kernel suite. The routines that we measure themselves are written in assembler, and we use 2 different benchmarks. One is intended to use latencies to local to all memory levels. In our case, the L1 data cache, L2, L3, and RAM, both on the local core and remote cores. And we were able to, we had a throughput benchmark which measures the throughput of SIMD instructions through the floating point units. And this is obviously limited by the bandwidth of the caches and the main memory. Therefore, we use that benchmark to analyze the cache bandwidth. So let's take a look at the results, starting with the latencies for accesses to the local cache hierarchy or memory hierarchy of a single core each. And we can see that both processors have pretty much the same L1 data cache latency. The L2 latencies are slightly higher on the Cascade Lake system, and a bit higher on the AMD system, although there's a caveat to the AMD latencies. We'll take a look at these later on. The main memory latencies on the AMD systems are higher. That's simply caused by the fact that the I/O die has to be accessed before the main memory can be accessed, which adds complexity to the data path and therefore latency. Let's take a look at the cache and main memory bandwidth we were able to measure. So in this plot, you can see the bandwidth for AVX and regular SSE instructions. And we were able to see that AVX instructions utilize the theoretical L1 cache bandwidth, and the SSE instructions come very close to their limits. SSE and AVX are almost able to saturate the L2 bandwidth, but the L3 bandwidth was not able to scale linearly with the number of cores. We are furthermore able to see that with this benchmark, at least on the setup, 3 cores were enough to saturate the bandwidth of a complete core CCD, which has 8 cores. So 3 cores are enough to achieve the highest bandwidth we are able to measure. On the Intel system, on the other hand, we saw a different picture. We used the AVX 512 base frequency of 1.6 gigahertz in order to avoid any kind of thermal power throttling. And we saw that no matter the SIMD width, we were below the theoretical L1 cache bandwidths. And furthermore, we saw a somewhat unexpected drop in the L2 cache bandwidth. So if you take a look at the figures for AVX 512, we measured 87.3 gigabytes a second cache bandwidth there for the L2 cache. And looking at, for instance, the AVX instructions, we would have expected pretty much the same number there because the L1 bandwidth was higher than the 87.3. So we had expected to see that the same number pretty much. On the SSE side, we have a number there for the L1 bandwidth that's way below the maximum L2 bandwidth we've seen for all SIMD width. And therefore, we would have expected to see identical L1 and L2 cache bandwidths for these processors, which was not the case. We've furthermore seen that the L3 bandwidth does not scale linearly with the number of cores as well. And we had to use 8 cores in order to saturate the main memory bandwidth, which is pretty much all the cores of a single subNUMA cluster. So let's take out the latencies when accessing remote cores, so cores that are, well, not the local core. And on the AMD system, we can see the very distinct NUMA characteristics. So the vertical bar represents one cache level with its cache states, and pretty much the darker the color gets, the further away the core is. And you can see that accesses to another CCX, even within the same CCD, take at least another additional 150 cycles. And then access to the main memory of another NUMA node take another 10 to 35 cycles, depending on the position. And that is pretty much the caveat with the L3 cache as well. The L3 cache has only the 39 cycle latency when you're within the local CCX. Once you start to leave it, you get the penalty of at least 150 cycles. The Intel system did not show these dominant NUMA characteristics. We are only able to see a latency of up to 5 cycles, a latency increase of up to 5 cycles when accessing a distant neighbor within the local SNC, and some additional 15 cycles when accessing the second subNUMA cluster. So not really a substantial compared to the AMD system. And this means that, for instance, the L3 is accessible for all cores with pretty much the same latency throughout the entire system. So let's get to the summary. The AMD system had very distinct NUMA properties, and the L3 can only be shared effectively on a CCX level. We've seen a very high floating point throughput per core, and we've seen that a low number of cores is enough to saturate the NUMA node bandwidth, which means that we have a very high per core main memory bandwidth. On the Intel system, on the other hand, we've seen that the 2D mesh monolithic design causes low latencies for remote memory accesses throughout the entire socket, which means that the L3 can be shared effectively for all cores. And we have, however, seen a floating point throughput that's below specifications and expectations. And we've seen that a high number of cores is required to saturate the main memory bandwidth. And with that, I thank you for your attention, and I'm happy to answer questions.
Thank you for the speaker. Very interesting talk. Very interesting presentation. There is questions from the manager on the Slack. His question is, how did you measure specific cache bandwidth? How do you ensure that your variables are in the specific portions of the memory hierarchy?
This is for both benchmarks use a comparable approach. Basically, they flush the caches before the measurement starts, and afterwards allocate memory buffers that are in specific sizes to ensure that they fit into the specific cache level. So there's a very well thought out access pattern to ensure that they are indeed in the required cache level or main memory level. Hope that answers the question, but we have gone into a bit more detail on that in the paper itself. So maybe that helps a bit.
Oh, thank you. And he has another question. The second question is, how did you measure the access latency?
Okay. So what we did, what the benchmark does is it allows us to specifically allocate memory at a different core. So before the benchmark itself starts, it initializes itself, and depending on the core configuration we chose, so for instance, access from core 0 to core 5, it allocates the memory at the respective cores with certain routines, ensures that the cache lines have the respective coherent state, and then pretty much just accesses the request memory from that core and measures the time for that. This is all done in assembler routines.
Thank you. I have another question. According to the characteristics of the two kinds of processors, do you have any advice to the hardware designer to help them make the better processors?
I think both processes are useful for very different approaches. So, for instance, the AMD addresses their, I don't want to call it an issue, but the situation with the L3 cache, for instance, in the current Zen 3 architecture. If I remember correctly, there are 8 cores all 8 cores within a CCD now share the entire L3 cache of that CCD effectively. So they are addressing the downsides to these things. And when it comes to the interprocessors, I think they have or their use generation will address many of the issues we've seen with these generations, or at least take a different approach with a multi-die approach. So they are certainly working on that.
Okay, thank you. That is the last question from the manager. The question is that, do you have access to the special API from the processor vendor, or did you use standard Unix system calls or some specialized Linux kernel functionality?
No, we don't have any special APIs. The benchmarks we used run on any well, at least Linux system, and I'm not sure about any Unix system, but they don't use specific APIs. This is all standard Unix and C stuff basically, or assembler instructions.
Okay, thank you. Thank you for your great presentation, and let's welcome the third presenter, Mohammad Majerza Sultani. I'm sorry, maybe my pronunciation is not right. Welcome.
Hi. Thanks, Yiming. Can you see my slide now?
Yeah.
let me just, hello, everyone. Thanks for being interested in our paper. Today, I'm presenting a smart rack, which is a near storage inference engines for AI recommendation system that uses a smart SSD. So I need to provide a quick background on the smart SSD architectures first. So a smart SSD is a new generation of computational storage devices that features an FPGA on board with the SSD. So this smart SSD allows the data to be directly transferred between the storage device, which is the SSD, and the computation unit, which is the FPGA. These smart SSDs provide three opportunities that we can use them for this AI-based recommendation system. First of all, this smart SSD have higher storage capacity than most of the DRAM-based systems, which allow us to use them for larger scale recommendation system. Second of all, because of the FPGAs on the board with the storage, the computation can scale with the storage. And lastly, because we have the FPGAs, we can customize the design on FPGA, which allow us to improve the energy efficiency of the design. I also need to provide some quick background on the recommendation system. So this recommendation system basically composed of two computation units. First, the blue ones are the fully connected layer or dense layer that feature many different neural networks, and also we use them in this recommendation system. And the other important operation in this recommendation system are embedding aggregation operation. So this recommendation system using categorical or sparse feature alongside with the dense feature. These sparse features are translated into dense features using tables called as embedding tables. The size of these embedding tables can be very large depending on the application and accuracy. But for each inference request, we only access a very few elements of the table, which makes a lot of random memory accesses to this embedding table. As a result, these embedding aggregation operations are more memory intensive in contrast to the fully connected layer, which are more computation intensive. Now, let's talk about smart rack, which tries to explore this smart SSD for accelerating this large scale AI-based recommendation system. There are three aspects that I want to talk about in this talk. First, we want to offload the computations of these recommendations to the FPGA and a smart SSD. Second of all, this is not enough. By offloading computation, we need to deal with the high latency cost of SSD accesses. And to achieve reasonable latency, we want to apply optimization, caching, such as caching technique to reduce the latency of the inference. And finally, we want to take advantage of the computational scalability of this smart SSD in order to build large scale system. Now, let's begin with offloading the computation. So as I mentioned earlier, the fully connected layers can be transformed into matrix-matrix multiplication. And in our design, we use a systolic array-based gem unit to offload this computation to the FPGA and a smart SSD. We also offload the embedding aggregation operation to the FPGA, which because of the fact that the FPGA can directly access to the SSD, this can be done effectively on FPGA. There are various options that we explored in our paper. The first option is what layers we can offload to the computation, to the FPGAs. One option is to offload all layers, including the top and bottom fully connected layer and embedding aggregation operations to the FPGA. We also consider other options, such as this slide showed. We partially offload some of the computation to FPGA and let the CPU do the rest of the computation. From a storage perspective, we also have different options on smart SSD. For a smaller size embedding table, we use the FPGA DRAM to store the embedding tables, whereas for larger embedding tables, we can use the SSD. Despite these opportunities, there is one main challenge for this SSD-based recommendation system. The fact that the latency of accesses to the SSD much higher than accesses to the DRAM makes the impacts the latency of the inference of this recommendation system. But thankfully, prior work has shown that there is a lot of data locality opportunities for accessing to these embedding tables, which by using a caching technique, we can exploit this data locality to improve the latency. Before I talk about how we design a caching system for this smart SSD, I need to provide a quick background on how this data transfer between the SSD to the FPGA. So there are 3 steps. The first step is that the CPU need to initiate the data transfer or the peer-to-peer data transfer. After that, without involving the CPU, the data can be transferred between the SSD to the FPGA DRAM, and then the FPGA can read the data from its DRAM and do the computation. Now, in order to minimize the cost, expensive cost of accessing the SSD, we want to use the FPGA DRAM as a cache for the data on the SSD. In order to do that, we need to divide the FPGA DRAM into 2 regions. One belonging to the data that are brought from the SSD to the DRAM through a peer-to-peer transfer, as I mentioned earlier. We cached some of these frequently accessed data into another region, which we call the cache region, for future accesses. But for any cache system, we also need to have some metadata in order to manage this cache. As we see earlier, since the CPU need to initiate all these data transfers, therefore we dedicate this job of managing a cache to the CPU, which therefore CPU holds this cache metadata and manage the cache with the software managed cache system. But the CPU also need to send extra metadata to the FPGA to guide the FPGA to find the data, either it's peer-to-peer regions or in a cache buffer. For more details, you can read the paper. The final aspect that I want to talk about is scalability. This large-scale system composed of many different embedding tables. One advantage of a smart SSD is that we can divide these embedding tables among multiple smart SSD, and by doing so, we can do the embedding aggregation operations on different FPGAs on different smart SSD. The good thing is all this smart SSD can manage by one single host CPU, which manage all these different smart SSD. Now let's talk about the evaluation. So we use a state-of-the-art recommendation model from Facebook called DLRM. So we use 3 different architectures which have different features, such as different embedding table sizes and different fully connected layers. We build our FPGA prototype using Xilinx Hls tool. And for the baseline, we use a DLRM PyTorch implementation running on a 22 cores Skylake machine with more than 700 GB RAM. So just a summary of some of the results that more results is available in the paper, but here I try to show some of the results that we basically explored. The first result that I want to show the inference time for the scenarios where data is in the FPGA DRAM. So we use different configurations, such as different number of a smart SSD and a scenario where the computation partially done on the FPGA, partially done on the CPU. As you can see, compared to the CPU for larger batch sizes, the inference times of the smart SSD is slightly worse than the CPU due to the fact that the memory bandwidth on the CPU is higher than the memory bandwidth on the FPGA on the smart SSD. We also explored the scenario where the data is in the SSD. For this case, the x-axis shows the hit rate, or basically what percentage of the accesses are hit in the FPGA DRAM. And the horizontal line shows the target latency set for this particular system. As you can see, when there is enough data locality, when the cache rate is high, even for larger batch sizes, we can perform within the target latency. However, for when the cache rate is low, then the execution times on this smart SSD slightly exceed the target latency. We also evaluate the energy efficiency of a smart compared to a CPU. As you can see, for different batch sizes and different number of smart SSD, we can improve the energy efficiency by up to 10 times compared to a CPU system. To summary, we explored various options to use this smart SSD for this large scale AI-based recommendation system. We propose optimizations such as a software managed cache for the smart SSD in order to improve the latency by hiding the high latency SSD accesses. We show that smart SSD can improve the energy efficiency by up to 10 times compared to a CPU system. And finally, we show that smart SSD can meet the target latency for this larger scale recommendation system when there is enough data locality in accesses to this embedding tables. Thank you.
Thank you for your presentation. Is there any questions from the audience? There is a question from the Carrie Williamson on the Slack. He said, nice stuff. When splitting an embedding table across SSDs, are the subtables disjoint, that is mutually exclusive size, would it make sense to replicate hot items from the embedding table across multiple SSDs to balance load, or would this undoubtedly complicate the lookup algorithms?
So I just want to make sure that I understood the questions. So basically, say if the size, if the embedding table sizes are not exactly the same, how we figure it out, like how we do this distribution between the different smart SSDs? Is that the question?
No, so the embedding tables, when you're splitting them and distributing across SSDs, do you split them up into disjoint sets, or do you replicate the popular items across the SSDs in parallel?
Oh, so basically in those DLRM systems, so there are like multiple tables which are totally like independent, right? So the way we do it is like we and at least for experiment that we did, all these embedding table have the same basically number of items and then the same basically sizes. That's why like we use very simple like kind of like, let's say the embedding table 1 to 4 goes to the smart SSD 1 and so on. So we didn't explore like if this embedding tables have different sizes or different basically features like that.
Okay, thanks for clarifying.
Okay, is there any other questions? Okay, let's thanks to the speakers.
Thank you.
And let's welcome the last presenter, Marius Sumit.
Yeah, hi, thanks,
Hi.
Yiming.
Yeah, hi. Can you share your screen?
Yeah,
okay.
I'm just sharing my screen.
Yeah, I can see it.
Okay. Okay. Good evening, everyone, and welcome to my presentation on Hls Profiler, non-intrusive profiling tool for HLS-based applications. Myself, Nupur Sumit, and my co-authors are Diksha and Manoj. We are part of TCS Research. HLS has eased the FPGA design development task by supporting development in high-level languages. Pragmas are an important feature available to performance tune the design. The HLS compiler reports an end-to-end latency, but line-wise cycle breakup is not available. For the C code example shown here, the developer doesn't get to know which part of the for statement is taking majority of the clock cycles. In the absence of this information, the designer cannot make out whether the current design is the most performance optimal and loses on the opportunity to improvise. A line-by-line association between the kernel code and performance can be used for fine-grained performance tuning of the source code. The concept of line-by-line association is not new, and its use is seen in software profiling tools such as gprof. But an equivalent profiling tool for HLS-based applications is not available but is highly desirable. One way to obtain line-by-line analysis of hardware design is through waveforms. Waveforms depict the temporal behavior of the design and is available only in terms of HDL signals. Though HDL code is the RTL representation of the source code, it can be quite involved to understand and necessitates familiarity with HDLs. This upsets the ease of coding benefit HLS development tools bring in, since eventually familiarity with HDL is required. Additionally, manually linking the RTL signals to source code signals is a time-consuming and complex task, especially for large designs. The highly parallel, pipelined, and data flow-based execution in FPGA designs makes performance accounting a challenge. Also, performance profilers are not available as part of commercially available HLS tools. With this work, we are making an attempt to bridge this gap with a framework that provides a performance profile of the generated RTL in terms of source code terminology. We propose Hls Profiler tool for profiling HLS-based applications. Hls Profiler takes C source code as input and generates its line-by-line performance profile. This information tells the developer how many clock cycles are taken to execute a certain line of code and provides a detailed view of source code variation at a cycle level granularity. Additionally, it indicates the amount of parallelism and pipeline realized by the design. With this information, the developer can quickly identify the performance bottleneck on the source code, track the program execution, and observe the effect of performance optimization in the form of parallelism or pipelining. Furthermore, such a profile is similar to what software profilers also report, and thus is easy for the software developers to understand and does not necessitate familiarity with HDLs. Here is the output of the Hls Profiler, called as summary report for an example source code. The trip count indicates the number of hits of a certain source code line. The line latency indicates the number of clock cycles taken to execute a certain source code line. Based on the line latency, line number 8 and line number 9 indicates the bottleneck operations for this source code. The line latency gives some indication of the performance bottleneck, but it doesn't account for parallelism, which is commonly seen in FPGA designs. The Hls Profiler captures the design parallelism in the form of weighted latency, which indicates the exclusive cycles or non-overlapping time spent on each line of source code. Based on the weighted latency and trip count, the exclusive line latency of the lines are calculated and indicated in red here. Additionally, the last column on overlapping lines tells us the line number with which the certain line is sharing its execution clock cycles with. The higher the number of overlapping with other lines, the higher is the parallelism in the design. Internally, the Hls Profiler is based on static information available from Hls compiler and dynamic trace available from co-simulation waveforms. The static information captures the data path control flow and helps draw associations between source code line number and variable names. The dynamic trace is indicative of the runtime design flow and associates a clock cycle and source code variable value. The basic static information and dynamic trace-based associations between source code and HDL signals are not absolute. we observed missing or incorrect linkages in cases where source code contains branches, shift operations, or duplicate statements. This behavior occurs because HLS compiler optimizes out sections of code or preemptively schedules certain operations to extract maximum performance. However, this upsets the correctness of the performance profile. We introduce associative rules to address such cases. The associative rules are based on source code semantics and plugs the incorrect or missing source code and HDL signal associations. Here we have presented some of the associative rules. Detailed discussions on these is presented in the paper as well as in the pre-recorded talk. We evaluated the profiler on an industrial recommendation application called NICER. NICER is an in-house developed recommender model developed in HLS since FPGAs can satisfy the fast turnaround time requirement of recommendation systems. The NICER algorithm contains many large matrix multiplication operations of the form of lin_a equation shown here. The source code of NICER contains 3 nested for loops with inner_mul and inner_add loops at nesting level 3. The inner_mul generates the product terms in matrix multiplication that are accumulated in inner_add loop. According to the performance profile obtained from Hls Profiler, inner mul is the bottleneck operation where 49.5% of the time is being spent. This time can be brought down to 4% when the developer adds array partitioning and loop unrolling pragma on this loop. This translates to an overall performance gain of 2.3 times for NICER. The state of the art in the profiler domain is now discussed. HLS scope focuses on estimating performance for HLS-based applications by introducing probes into the design, and the profiling is done at loop or subfunction level. Other works such as Comba, Aladdin, and Lin Analyzer uses instruction tree trace to estimate program performance. These works focus on providing analysis for efficient design space exploration by limiting synthesis runs, but struggles when the design contains multiple interdependent pragma directives. HLS Profiler, on the other hand, is non-intrusive and does not consume any hardware resource of the FPGA. It is based on cycle-accurate simulations available as part of HLS development tools. This helps in getting a cycle-accurate profile without the need of actual hardware run and avoids a time-consuming step of bitstream generation for the FPGA. On the other hand, state-of-the-art tools use performance estimates and does not take into account the simulations. Additionally, HLS Profiler captures the amount of parallelism through the overlap of source code lines. This is a desirable parameter in the profile, especially in highly parallel designs, the likes of which are often targeted on FPGAs. Since the output is in human-readable format, it is user-friendly and exhibits similarity to software profiling outputs. Because of these reasons, the profiler can be used seamlessly by software designers without necessitating familiarity with HDL domain knowledge. The profiler is not without its assumptions and limitations. These are discussed in detail in the paper as well as in the pre-recorded talk. In conclusion, profiling an HLS-based design is challenging because of the inherent parallelism of the FPGAs and requirement of domain knowledge while using traditional methods. Our work on HLS Profiler bridges this gap and provides a performance profile of the generated HDL in source code context that is easier for the designer to interpret and identify code hotspots. The profiler builds on the static information and dynamic trace available from HLS development tools. In addition to this, the proposed associative rules help plug the incorrect and missing associations in profile that are seen when using only static or dynamic information. HLS Profiler is non-intrusive and as a result does not consume any hardware resources. Additionally, it does not require actual hardware runs to create performance profile since it is based on cycle-accurate simulator output. The analysis of Pragma-enabled source code is a work in progress for us, and we have new associative rules to address them in the current version of the tool. Also, in addition to performance, analyzing other constraints such as area and power can provide a holistic feasibility view of a certain design point. We wish to incorporate such constraints in future versions of the tool. This brings me to the end of my presentation, and thank you for your attention.
Oh, thank you for your great presentation. Is there any questions from the audience? Okay, I have a question. It seems that you made a tool, so I'm curious about the usage and the performance of this tool. That is, how fast and easy to use your tool.
Right. So the Hls Profiler for comparatively simple single for nested for loops and which the source code that doesn't contain multiple subfunctions, we are able to generate the profile in a couple of minutes. But for a little bit complex codes, it does take a little bit of time for the profile to get generated. And I understand it's a bummer, but then we are working on increasing the performance of the profiler tool. And there's a good reason that why currently the profiler is slow. That is because the processing is done at a cycle level granularity, and we go cycle by cycle while actually creating the profile, generating the profile. So yeah, those are some of the reasons that the profiler is currently slow, but then we are working towards improving its performance.
Okay, thank you. Is there any other questions? Okay, thank you. Thank you for everyone, and especially for the speakers. If the audience have the questions in the future, you can leave your questions on the Slack. Today's live session is over. Thank you so much. Bye.
Thank you to Yiming and all the speakers. So we now have a break until 4:25, I believe. Yes, 4:25, and then we will continue with the work in progress in vision track. Christina, are you already around? I see you at least. Yeah, we will continue in 10 minutes.
Hi, are the presenters for the next session here? I think they are Gagan and Marius.
Yeah, I'm already here.
Yes, that's great. Thank you.
Hi, Christian. I'm also here.
Yeah, that's good. And can you just confirm that both of you are seeing the share screen available in your Zoom?
Yes, this is the case.
Okay,
yeah,
that's good. We'll wait until 9:25 to begin.
Sure. Thank you.
Okay, hello, welcome everybody to the work in progress and vision track of the ICPE 2022. We have two exciting work in progress papers today. As these are shorter papers, the presentation is also shorter. We'll have a 5 to maybe 7 minute presentation. If you need a couple of more minutes, that's okay. And then 5 minutes for questions. Just remember that if you want to ask a question, it is better if you post it in the correct Slack channel. But you could also, if for some reason you don't have access to that, you could also then raise your hand or unmute yourself once we are in the question section. But just to have a record of them, if you do have access to the Slack, that would be preferable. So our first presenter is Marius Hadry, and he has an exciting work today for us called Faith. Marius, can you please share your screen?
Yeah, sure. 1 second. Okay, now you should see my presentation.
Okay. Perfect. Yes, go ahead.
So thanks for the introduction. My name is Marius Hadry, and I am going to present my vision paper with the title Towards Flexible and Adaptive Distance Estimation. This is the joint work of Veronika Lesch, Samuel Kunev, and myself. All three of us are from the University of Würzburg in Germany. So first of all, I'd like to start with a little introduction of an illustration of a facility location problem. Right here, we can see a facility that we want to place to match the customer needs around it in the best possible way. Such problems are usually solved using optimization algorithms, and they work by moving this facility around and trying different locations. Then the costs are estimated that are required to serve all the customers, and this is usually done by including some kind of distance measurement. And there we often rely on mathematical functions like the great circle distance, which is simply the line distance between two locations. This is actually pretty fast, but is also inaccurate in the case where obstacles are in the way. And we try to find something in between so that we do not have to use street networks to calculate the actual distance, because this again is then too slow, but would be fine accuracy-wise. So FADE aims to be in between those two things and is a trade-off between the accuracy and efficiency. And we aim to achieve this by using a simplified graph. Right here, we can see the approach on a higher level. I will just give a short summary of it. If you're interested in more details, I refer you to our paper or the longer YouTube video. On a higher level, we divided this approach into a pre-processing phase and an estimation phase. During the pre-processing phase, we start with collecting detailed map data. In our case, we used OpenStreetMap data because it is freely available. This data is then filtered, so only the data relevant for our use case remains. We only considered water areas and bridges, hence we can see here there's only the river remaining and the bridges that are usable by cars or other vehicles. And this abstract map was then the base for the next step, where we create a passability graph. To create this passability graph, we applied a grid to the abstract map and analyzed each individual field within this grid for the passability property. So in case there is a chunk of the river within a field, we marked it as obstacle. And if there was a bridge or no river, we marked it as passable. Then this grid, or each field within this grid, was converted into a node. And nodes that were obstacles were colored black, and nodes that are passable are colored white. And white nodes are connected to other white nodes in their neighboring. So this is the creation of the passability graph, which is then the graph that is used during the estimation phase. And if this graph is created once, we can reuse it all the time. To actually estimate the distances, we simply place facilities within the graph. So we select the nodes of the fields where the facility would be placed. And instead of calculating the line distance, which would cross the river, we can choose to walk across the bridges, which makes this a little more accurate. Those paths can be found applying classical graph algorithms like Dijkstra's. We then implemented this procedure in a little prototype, and right here we can see the first evaluation results. For the distance, we can see that the Haversine or great circle distance, which is the line distance, is worse than our approach, but the actual road distance is, of course, the gold standard and hence the most accurate way. But we can also see that the calculation in milliseconds of clock time were much slower when we used the street graph compared to our approach, while the mathematical functions were much faster. Okay, so next I'd like to present the outlook for fate. Currently, our prototype only supports a static grid size, and we plan to adapt the field size within the grid in the future based on different parameters. For instance, we could choose to analyze the population within various fields and choose smaller field sizes within highly populated areas so that we can further reduce the number of nodes in areas where that are less populated. We further want to introduce a gradation between the passable and obstacle property so that we can allow a different edge weights based on the terrain. For instance, if we have areas where serpentines are pretty common, we plan to use different edge weights so that we can account for things like that. The last step we want to integrate into our approach is the user specifications, so that users can define the level of accuracy they require and also the level of efficiency they need. Based on these inputs, we plan to learn the grid composition to further match the user's needs. And to achieve this, we aim on applying self-aware computing concepts like the LRAM loop depicted here in this figure. Okay, this concludes my talk. I'm happy to answer your questions if you have any.
Thank you very much, Marius. That was great work. Any questions from the audience? Okay, so while people gather their thoughts, I have a question for you. Do you think there could be other applications, I mean, maybe in this same domain with some differences or in other domains of your technique?
Yeah, of course. I mean, this work is based on another work where we try to develop an optimization algorithm for a facility location problem, and we ran into exactly this problem that we had rivers in between, and the mathematical function was too inaccurate. But using street distances or other distance functions was not feasible. So this is where the idea comes from. But in the end, it doesn't matter where you want to apply any kind of distance measure. I assume you could always use this approach.
Okay, thank you. And I think, hold on, like somebody had unmuted. Okay. What would happen if you applied the technique and in the case that actually the whole map is passable? And then like, would it be too slow or would it still work?
I mean, it would still work. But if we just go back a little, if we did not have that river right here, we would simply more or less approach the line distance with our calculation. I mean, we would still be limited to the edges we inserted, but yeah, I think if we already know that there are no obstacles at all, it would make more sense to just use the mathematical functions.
Okay, thank you. And you also mentioned other techniques that are used in this kind of problems. Are these orthogonal to play? Like, could you combine this with your approach?
What do you mean by other techniques?
Like, for example, what you're comparing here against fate. Could any of these be combined, or they're completely like different types of solutions?
Applying this simplified graph is pretty different from using those mathematical functions, but of course there are graph theoretical algorithms that could always be applied to our graph. So that might result in speedups in this case. Furthermore, the grids have relatively large size. So we could also think about integrating a mathematical function in the first step to reduce some kind of offset error.
Okay, I see. Thank you. So we do have time for one last question in case anybody has a question for Marius. Okay, so if you do come up with a question later, oh, sorry, no, that's Gagan. Okay, if you do come up with a question later, we can still use Slack, and I'll ask the presenters to keep monitoring the chat. And so the idea is that we can keep the discussion going if there's any interest in that. So thank you very much, Marius. Marius. And now we will see a presentation by Gagan Somashekar, and he's presenting his work called BMEG. Go ahead, Gagan.
Thanks, Christian. Can you see my screen?
Yes.
Yes, thank you. Hello, everyone. I'm Gagan. I'm a PhD student at Stony Brook University, New York, and I am advised by Professor Anshul Gandhi. Today, I'll be talking about our work on detecting bottlenecks in microservices applications using graph neural networks. This work was done in collaboration with Anurag, Rohit, Bhargav, and Anshul. Microservices architecture, due to their various advantages, are replacing monolithic and multi-tier architecture. Since most of the applications implemented using this architecture are customer-facing applications, the performance is crucial. Accordingly, detecting and mitigating performance bottlenecks is paramount. With microservices architecture, the problem of finding bottlenecks is exacerbated by the following. Due to the complex interactions that exist between microservices in a microservices application, it is difficult to precisely pinpoint which are the bottlenecks. Data-driven approaches have shown promise, but it is difficult to employ them as there is scarcity of labeled data in production system. Even if we are successful in getting some labeled data and we train a model to learn the bottlenecks, the frequent updates that happen in microservices applications, the dynamic nature of the call graphs, all of them make it difficult to have a generalized solution. So this begs the question, how to precisely pinpoint bottlenecks using limited labeled data in a generalizable way? We believe graph neural networks are the way to go about this. So what are graph neural networks before you get into the why? Graph neural networks are neural network models that learn representations on graph structured data through feature propagation and aggregation. And why does it fit here well? So we have an ample amount of natural graph data through call graphs when it comes to microservices applications. And GNNs have shown superior performance on graph data. I talked about how there is complex interaction among nodes, among microservices in an application. And GNNs are very well suited to learn dependencies among these nodes. The unavailability of label data leads to multi-class imbalance problems, which GNNs are known to handle well. GNNs are also known to generalize well through transfer learning. All these features make them a very good fit for this problem. Coming to the problem statement, we divide the problem of detecting bottlenecks in microservices application into two stages. The first stage being detecting anomalous traces. Anomalous traces are traces that are affected, are the traces that are affected by the presence of bottlenecks. The second stage being detection of bottlenecks in such potential anomalous traces. We transform the problem of detecting anomalous traces into graph classification problem. That is, we take a call graph and we classify whether it has anomalous trace or not. And the second stage is transformed into a node classification problem. So the nodes are the microservices, and we classify whether a node is a bottleneck or not. To perform these two tasks, we use two different models that are based on GNNs. The first being the graph classifier, which is DGCNN the architecture from the ICML 2020 publication. And we use a vanilla node classifier using GCNs. The roles of each of these layers are discussed in the paper. I've briefly presented the architecture here for reference. Coming to the dataset, we use the firm dataset that was published as part of OSDI 2020. This dataset consists of traces of Death Star Bench framework, Death Star Bench benchmark, and also the train ticket application. Each trace in this dataset consists of a single bottleneck induced via artificial interference. One of the main goals of this work in progress work is to evaluate how well a GNN-based model performs on imbalanced dataset. Accordingly, we randomly sample traces from the firm dataset to create three datasets A, B, and C. The percentage of traces that contain bottlenecks is given in the brackets. So for example, dataset C contains 99% of traces that do not have bottlenecks and 1% traces that have bottlenecks. Coming to the preliminary results, the graphs here are for the social networking application. We compare our framework BMEG against SVM. The metrics that we use are accuracy, precision, and recall. NB in the graph stands for non-bottlenecked, and B stands for bottlenecked. So, and important metrics, values of important metrics are given above the graph. But just to summarize, the results are discussed in detail in the paper, but just to summarize the results, BMEG maintains a good balance between precision and recall for complex graphs that are usually seen in social networking application, even when the dataset is highly imbalanced. On the other hand, for simple graphs, which are seen in media microservice, hotel reservation, and train ticket, the SVM does outperform BMEG as it is easy to learn thresholds in such simple graphs. I just stated the conclusion in the previous slide. So the BMEG's performance motivates us to explore it more. And coming to the future work, we want to evaluate how well GNN-based models generalize through transfer learning. And I talked about how the dataset only has a single bottleneck per trace. So another future work would be to create and open source traces that have multiple bottlenecks. We also want to analyze the impact of dataset size on performance and training effort. And lastly, we want to compare against other related work and application performance management tools like AppDynamics. Thank you.
Thank you, Galian, for your presentation. It was very interesting. Are there any questions for the presenter?
I'd like to ask one.
Yes, thank you, Mark.
I'm not familiar with the data set. I probably should be. But does the data set include data on internode traffic, on traffic between microservices, or only data about the microservices?
It has data on the service time of each microservice.
That's all. So it doesn't talk about the number of bytes transmitted between microservices.
No, yeah, it doesn't, yeah.
Okay, thank you. Any other questions? Okay, I have a question. So I think it's definitely, I agree with you, this is definitely a very real problem because like you showed, these applications can become quite complex in large companies, but also I guess in other smaller companies as time passes, the complexity keeps adding. So finding these bottlenecks is definitely important. But I was wondering, how do you envision that BMake would be used in practice, or where would it be implemented, like at the orchestration layer, at the monitoring layer, at the application layer?
Yeah, that's a really good question, Christina. So I think this, I think, would probably be well answered once we have data on how much, for example, the inference time. If the inference time is very less and we are able to get a good performance at a very low inference time, then I think it would be used in real time during monitoring itself, instead of just at the orchestration level where we take pre-deployment decisions. We could take real-time decisions as long as the inference time is less.
I have a follow-on question, Gega. In bottleneck situations, it's normal that there can be a bottleneck behind the bottleneck. That is, if you relieve one bottleneck, immediately another one appears. And it's possible in some situations to detect both of these. That is, to be aware of all the cascading bottlenecks. Do you feel that your model, that your GNN tells you that information, or does it only have to uncover one bottleneck at a time?
That's a really good question. Yeah, I think that's one of the motivations for us to create a data set with multiple bottlenecks. For the current work, these traces only have a single bottleneck. So we are restricted by the data set in a way to say whether the model does well or not. Each trace has only a single bottleneck right now. So yeah, that's a limitation of the data set. And that's something I think should definitely explore. Yeah. Thank you.
Very nice work. I like it.
Thank you.
Thank you, Marius, for the question. More questions from the audience? Okay, so I had some questions that maybe you could clarify or give a little bit more information on the training process. Like, for example, how sensitive it would be to the choice of anomalous traces that you use for the training. Things like, I mean, maybe you could have traces that you think are anomalous, but maybe they aren't, or like the time or period that the trace captures, like whether it's sensitive to a trace that has a lot of time before and after the anomaly and things like that.
Yeah, I think that's a nice question. I think with the three data sets, in a way, we kind of evaluate how well would it perform based on the proportion of data sets. But yeah, we do assume that the labeled data set that we get is the ground truth. So assuming that that's the ground truth, if the proportion of, we vary the proportion of traces with bottlenecks and without bottlenecks. And what we see is, yes, the performance is better when there is some balance between the number of bottlenecked and non-bottleneck traces. But even for the data set with only 1% of bottleneck traces and 99% traces which do not have any bottlenecks, it does maintain good balance between recall and precision, although the performance is not as good as, say, if it was balanced.
Okay, I see. Thanks. More questions from the audience? Okay, so if we don't have more questions, again, you can still post them on Slack and the presenters will be checking there. And we should now thank Marius and Gagan for their very nice presentations. And with that, we can conclude the session. Thanks.
Thank you, John.
Thanks, everybody. So this brings us to our last break of the day until 5 p.m. European time. And we will start the last session, Theory of Performance. And after that, we will have our closing session.
Just wondering, how many hours from now?
Oh, hello.
Sorry, you go again.
How many hours from now?
You have Do you have a cancellation?
10 minutes from now.
Yes.
Okay, thank you.
What time?
Hello, everyone. Just checking if the presenters are. Hi, Andrea. How are you?
Hello, Maria. All good, and you?
Good, thank you. You're in class.
Nice to see you here. I'm in office, yes.
Okay, nice. Hello,
Hi,
Carrie.
Karen.
Hello, former
Hello.
collaborators. How are you doing?
Good, thank you. How are you?
All good.
I'm good. It's a bright and early morning for us in Calgary. A nice sunrise, but should be a good session to close the conference. Looking forward to your talk, Andrea.
Same here. We have snow in Calgary.
Snow?
Yes.
Well, Venice has a beautiful, beautiful weather now.
Yeah, you make us envious. Okay, checking. I see Adnan is here, and checking if yeah, I see Stefan. Hello, Adnan.
Hello.
Hello, Stefan. Okay, everybody is here. Everybody has audio, video. Wonderful. So we'll start in about 4 minutes. Just checking in advance to make sure everything is going well. Thank you all.
Maybe I can try to share my screen to see.
Yes, that would be great. That works.
That works. Okay.
Yeah, Adnan and Stefan, if you would like to try it right now, that would be
okay.
Good too. Yes, that works. Making it full screen would be, at the presentation time would be great. Stefan, would you like to try it or you're good? Okay, you're doing it. Wonderful. Stefan, just wanted to let you know KTH is my alma mater for my master's, so I'm very happy to see a talk from KTH. Hello, Murray.
Hi.
Hi.
Hi to Murray as well. Long time no see.
Hi, Gary. That's right. Maybe next year.
Yeah, let's hope so.
Yeah.
I know there is rivalry between Chalmers and KTH. I am assuming Philip's comment is with that regard.
Just a little bit of friendly rubbing every now and then.
Yeah. Okay. Time is 9 o'clock, our time, Mountain Time, and I believe that's 5 o'clock in European time. So welcome everyone, and We'll start our sixth session, Theory of Performance. We have 3 exciting papers in this session. Let's welcome our first presenter, Andrea Marin from Università Ca' Foscari in Venice for the paper, A Mixed PS-FCFS Policy for CPU-Intensive Workloads. Andrea, please start when ready.
Thank you very much for the introduction, Mariam, and good evening, everyone. I'm Andrea Marina, and I'm presenting this work, which is a joint work with Simonetta Balsamo, also at the University of Venice, and Lisa Mitrani from the University of Newcastle. So let me begin with some recaps that are very well known about the queuing theory, but they are the basis of this talk that I'm giving. So if we consider a queuing system with FIFO disciplines, so the jobs are served in the order of arrival, we know from the theory of queues that if the coefficient of variation of the service time is greater than that of the exponential distribution, then the MG1 with FCFS discipline has a response time, an average response time that is higher than the response time of the MG1 equipped with a processor sharing discipline. The expected response time is exactly the same if the coefficient of variation is 1, while if it's lower than 1, the first come, first served discipline is better than the processor sharing. The processor sharing discipline has the advantage that it enjoys the so-called insensitivity property. It means that the stationary behavior of the MG1 PS system is basically insensitive to all the moments of the service time distribution higher than the first. And the behavior of the MG1 PS system is basically has exactly the same expected response time and utilization, everything of the MM1 queue. This is very important because if we are not aware of the distribution of the service time, this gives us some kind of guarantees on the expected performance measures of our system. The round-robin scheduler implemented by many operating systems is considered in general a good approximation of the processor sharing because it shares the computational units among all the processes that are in the ready state. So let me show a picture of how is the expected response time with respect to the coefficient of variation. This is an example. And here we have the maximum service rate. We assume that it's going to be 1. And here you may see that the arrival rate increases, and then we have this vertical asymptote that is the same for the MG1 and the MG1 PS system, but the line of the MG1 PS stays always below the other two. So suppose now that to implement the round-robin scheduler, we have a cost for context switch. We will be more precise about this cost later on this presentation. Right now, suppose that it costs 10% of the service rate, okay? So in this case, it's clear that the MG1 PS system becomes convenient in a certain region of operating of the queue, so in low and moderate regimes, but on heavy load, we prefer to avoid the context switch and the cost of the context switch and to resort to a first come, first served discipline. So this is an oversimplified intuition of what is going on this work. So the real world slowdowns for round robins are more complicated than just saying 10% of the service rate, of course, because it depends on many factors. Basically, the cost of context switch are usually divided in two parts. One part are called the direct cost, which are the cost of making the context switch, changing the context of the process running. And in modern architecture, these costs are very, very small. They're almost negligible. Then you have another cost that are called the indirect cost of the context switch that are due to the fact that you're using some resources like the cache. And when you do the context switch, part of the cache usage can be trashed, can be not anymore usable by the restoring of the context of another process. Okay, so that's basically the cost of the context switch. Moreover, some schedulers, like the completely fair scheduler on Linux, they tend to reduce the time slice assigned to a job as the number of jobs grow, and so you have more context switch when there are more parallel jobs in the executing phase. So what's the contribution of the work? We propose a scheduling in which you have at most n jobs in parallel, and the remaining one are in first come, first served discipline. This is not a new idea. To the best of our knowledge, it's the first time that it's been modeled and studied. But for example, if you consider Apache, it works exactly like this. You have a maximum number of forks that can be done, and the remaining request waits in the first come, first served discipline. So the research questions are, the first is if we preserve the insensitivity property of the processor sharing, or the fact that the first come, first served discipline depends only on the first and second moment of the service time, when we mix these two disciplines. And the second point that we address is if we can determine the optimal value of n to minimize the expected response time, and then we want to do some tests to see how the system behaves on real workloads. So the assumptions are the usual assumption for Markovian queues with Poisson arrivals. The service time is Coxian with an arbitrary number of phases. In this way, we can approximate arbitrarily well any service requirement. We have an infinite buffer, and the slowdowns can depend on the number of current jobs that are sharing the processor. We propose two solution methods. Each of them has pros and cons. I invite you to listen to the longer presentation for a description of this. One is based on generating function, and one is based on quasi-Burton depth process solution. So the first things that we found surprising is the sensitivity analysis result. So we know that the first come, first served discipline is sensitive only to the first two moments of the service time distribution, and the processor sharing is sensitive only to the first moment of the service time distribution. The interesting thing is that when we combine the two disciplines, we have a sensitivity to moments that are higher than the second. We found this result very surprising. It's true that to emphasize this result, we have taken some parameterization of the service time that is designed to show these aspects in a very evident way. And for practical purposes, you can say that it depends on the first two moments, but it's interesting to see from a theoretical point of view that instead there is a high sensitivity to higher moments. Then for the determination of the optimal value of n, now we will show how we do it. We basically use the bisection methods. And for example, in this experiment, we assume the slowdown function that we took from the literature. And here you get that, as you may see, here you have the expected queue length on the y-axis, the number of parallel jobs that you put in service, the maximum number of parallel jobs that you put in service, and you may find an optimal value for the parallel level. And the interesting thing is that, of course, if you have a higher variance of the service time, you expect to have a higher optimal value for n, because you need a more higher level of parallelism to serve the jobs. Then we have the experimental evaluation. So in this setting, in this experiment, we ignore the direct cost of context switches. So we just pay the cost of trashing the cache. The cost of context switch is taken also from the literature, and it's like 500 microseconds. And by combining this value, we obtain this slowdown function here. The job sizes are taken from the literature and are with a bounded Pareto distribution from 1 second to 10 to the power of 6 seconds, 1 million seconds, with a parameter alpha of 1.2, and we fit these into a Coxian distribution. So this is the result that we obtain. As you may see, as n grows, we have that we obtain an optimal value of n when the load factor increases. When the load factor is low, basically with a very few number of parallel processes, even if we have a very heavy tail, it's going to be optimal for the minimization of expected response time. The setting of the second experiments, instead, we have a fixed time slice, while the one before were done with the time slice that were becoming smaller and smaller with a number of processes that were more present in the memory. And so we got a slowdown function that has this shape here. And we got this plot here. Let me discuss this plot because it's interesting because basically,
Andrea, just 1 minute. Thank you.
It's finished, yes. And here you may see that we have a decrease of the performance with respect to the first come, first served, because here basically we are paying the cost of the context switch, but we are not getting the benefits of the processor sharing because the level of multi-programming is too small. So it's the model can help in finding the good value for n because it may even wash down the performance. Okay, this is the conclusion. So we show this discipline, which is a combination of processor sharing and first come, first served. And basically we have that we can set up the maximum number of jobs that can be served in a processor sharing fashion. We observe that for the practical scenarios that we considered, this value of n is lower than 15 or 20 for workloads that we've taken from the literature. There is a trade-off clearly on setting n, because if you take a large value of n, you need many resources for handling the parallel computation, while for low value of n, you have a problem of cache coherency without improving the expected response time significantly. And the QIM model can be used to determine the optimal value of n. Thank you very much.
Thank you very much for the great work and for the great presentation, Andrea. There are questions in the chat. I'll read Carrie's question. Very nice work in the optimization. Is the value of n a static, or can you dynamically change n as well?
You can dynamically change as long as you can, you accept to compute it. So it basically depends if the effort of the computation of the optimal value of n is comparable or not with the service time of the jobs. The model can be solved quickly. And by quickly, I mean that, for example, if you use the quasi-Burton that process, the convergence of matrix R and so on will take you a couple of seconds. So if you're handling jobs where service time is sufficiently larger than this, then you can run it as a dynamic optimization, and you can even change the optimal value of n according to the load factor that you have in the queue. But of course, if in case the jobs service time which is comparable to this, you don't want to consume resources for optimizing the value of n in this case. I don't know if these answers the question.
Thanks.
Yeah,
good to know.
The next question is from David. I see you have turned on your camera. Would you like to ask it yourself, David?
I mean, you have nice results on what I assume are the average response times. I was curious if you had any insight from the work about the impact on like the tail latencies, you know, the slowest of the slow, which is often what we end up caring about in production systems. You know, how long do the slow ones take?
let's say that we've not directly studied this, and it could be an interesting thing to analyze, to focus on this aspect. Let me give you an informal answer to this question, and I hope that it will satisfy. So the key point here is that the processor sharing has this average response time, which is very nice, and it is insensitive to moment higher than the first. And usually this is explained by the fact that while in the first come, first served discipline, if a small job finds at its arrival time a big job in front of the line, its performance is bad because it has a long waiting time. If it happens the same in a processor sharing system, the small job is going to be served in parallel with a big one, and so its performance, it suffers, but not that much. Okay, so in this case, what we are saying is that this effect on performance is bad only if when you arrive, you have, say that n is 15, you have 15 jobs that are occupying the server in front of you that are big jobs. And so you have small jobs and you suffer the waiting time as in the first come, first served discipline. So my answer is basically this. If you want to observe the tail of the jobs, and it's a large job, it's very likely that you will get something which is very similar to the processor sharing, because the large jobs, it will enter in the system and in the parallel processing, okay? And it's going to occupy the place as if the small jobs don't interfere too much with them. So the problem is more for the small jobs that if you choose an n which is too small, they could file all the slot of service occupied by the big jobs. I don't know if this helps the intuition about the answer, but we don't have a mathematical question about this, so I could be disproved by equations, but it's just an intuition that I have to answer your question.
Okay, thank you.
Thank you very much, Andrea. Let's move on to the next presentation in the interest of time, but the discussion can continue on the Slack channel. And if we have time at the end of the session, we can come back and ask more questions as well. Stefan, let's welcome our second presenter, Stefan Collin from KTH and Scania in Sweden for the paper, A Stochastic Extension of State Flow. Stefan, please start when ready.
Thank you. And I trust you hear me all right. All right. So my name is Stefan Collin, and I'm here to present our paper, A Stochastic Extension of State Flow, which I wrote together with Anton Hampus, Mattias Nyberg, and Ole Mattsson. And this was a collaboration between KTH Royal Institute of Technology and heavy vehicle developer Scania. So first I will talk a bit about model-based development in industry today. So systems are today growing increasingly complex, something that is pushed on even further by new technologies such as autonomous vehicles and the like. And as systems has grown increasingly complex, model-based development has become an integral part of research and development in general. Now, within the industry, one tool that is very well used for model-based development is Simulink State Flow within Scania and within MATLAB. And this is a very well spread tool, as I said, for example, in the automotive industry. Now, to perform model-based development, for many purposes, probabilistic properties are very important to be able to have new models. One such application is when you're working with safety. Now, our goal with this paper was to extend state flow with probabilistic properties. So first I will talk a bit about state flow in general. So state flow is within Simulink and MATLAB. And MATLAB is a language and environment for technical computing with more than 5 million users worldwide. And state flow within MATLAB is a tool for modeling state machines. And it has become an industrial standard practice in many areas, for example, the automotive industry, as I mentioned. And it has explicit support for temporal time-dependent properties, but it does, however, not hold explicit support for modeling stochastic properties. And as I mentioned, those are vital, for example, within model-based safety analysis. And there are, of course, other tools which can be used to create models with stochastic properties. However, they lack the wider spread in industry that Stateflow has. To begin to talk about our stochastic extensions, I will first talk about how Stateflow looks today. So we'll go through the syntax here real quick. So firstly, our extension of Stateflow is built on a subset. And this has been chosen by studying a lot of case studies to find what's most important to be able to do in the models, and also in the spirit of using a safe subset of Stateflow. And the main limitations of this subset is that there are no variables and there are only one type of events. So these are the main changes from the complete Stateflow. So just shortly, how does Stateflow work? Well, it can look something like this, a Stateflow model. So we have a bunch of states, as you can see here, and we have a couple of transitions within them. We also have some default transitions here, which says that if we enter S1, we will also enter S10 and not S11 by default. For example, as you can see, the states have different lines around them, and that depends on if there are or and states. So whether we are in both S1 and S2, which we are, which is why this is the dashed line here, which means that, as I said, we're in both S1 and S2 at the same time. These are parallel. But if we within S1 here is just in one of its children states, then we have draw a hard line to show that. Now, a transition typically looks like this. We have three parts here. We have a set of condition events, we have some kind of guard, and we have a broadcast event. So when we enter the source state, S8 here, for example, the clock for this after expression starts counting down from 1 second. And when the time has been reached, this guard is evaluated to true. But for the transition to happen, both the guard needs to be evaluated to true and one of its condition events need to be received. So for this particular model, what will happen is that this clock would run out after 1 second, but this transition would not be made yet because we went waiting for an event. Then after 1 more second, so a total of 2 seconds in the system, this guard will be evaluated to true. There are no condition events, so this transition will happen. And when it happens, it broadcasts the event E1, which is received here and will cause this transition to occur as well at the same time. Now, for our stochastic extension then, and we call this stochastic state flow, SSF. And there are 2 major changes here. So we extend with probabilities in 2 ways. So as you can see in the after expressions here, we allow not only to have these types of clocks that Stateflow have, which says that after a certain amount of time this will happen, but we can also have a probability distribution, which simply says that when S3 is entered, this guard will be evaluated to true after some time, which is log normally distributed with parameters 2 and 1. Otherwise, the events work the same way. We also have probabilities in one other way, which is what we can see here. So if we are in S4 here and receive one of these condition events, then this transition is triggered. And using this junction, which we call this one, we can then find that with probability 0.8, we will end up in S5 and will not send an event. And with probability 0.2, we will end up in S10 and we will broadcast the event E3. So to summarize, we add probabilities and stochastic properties in 2 ways. These probability distributions for delays and these probabilistic choices about where you go and what you broadcast. And we also presented in a paper extensive operational semantics for SSF, and this was quite a bit of work. Stateflow has a complex semantics within itself, but it generally works by describing how configuration changes when something happens in the system. And here we just have a sample And a configuration is basically a set of active states and an evaluation of the timer. So of the probability distributions, you get an actual value of it. And here we see, for example, that if we broadcast the empty event, so if we don't broadcast any events, then that will not cause change in configuration. However, if we broadcast some events, that may change the configuration in some way given by another rule. And to see the complete rule set, look in the paper. As a second contribution, we implemented support for SSF models within the SMP tool. And with that, analysis can be performed of SSF models which have been modeled in Stateflow. So we can perform, for example, transient analysis and sensitivity analysis. For more details, read the paper. And as a third contribution, we presented a case study from Scania, which we call the gearbox wheel lock. And that's about different gears in the gearbox locking in when they shouldn't, which causes the wheels of the vehicle to lock up when you're in driving. So your driving wheels can suddenly lock in their current position. And that's, of course, something we want to avoid. So we wanted to compute what the actual probability that this will happen. And this is what we have tried to model here. For details about the model, I again refer you to the paper. But what we could do with the SMP tool is then, for example, that we can perform a transient analysis. So here we looked what happens after a lifetime of 45,000 hours of a vehicle. What's the actual probability that we will have this wheel lock? And we found here that the probability was about 3 times 10 to the power of -7. And it's based on simulations, so we get a confidence interval. So the 95% confidence interval is all below 5 times 10 to the power of -7. So then, of course, you need to set a goal, a requirement for how safe does this need to be? What's the worst we can allow? And then you can find, does our system actually uphold this by creating an SSF model and analyzing it using the SMP tool. Now that was all I had today, but for any more details, contact me or read the paper. And are there any questions?
Well, Stefan, I might try one.
Shoot.
This is you use simulation-based analysis.
Yes.
So, and you compare to more limited modeling capability, which is based on Prism,
yep.
which is analytic, which is numerical Markov chain analysis, not exactly analytic. But
yep.
So the advantage of the reason that Prism was developed rather than depending on simulation was the analysis time for problems. That is, it's faster to solve Markov chains numerically than to simulate them. Do you have any feeling for the ratio of analysis times between the Prism-based approach and your simulation-based approach on a similar problem?
Yeah. So first, I should mention that for some subsets of SSF models, we also have a symbolic/numerical engine within the tool. But that is very dependent on the model when how much worse simulation is than numerical analysis. I mean, generally, if the expected number of transitions within the model are very high within the lifetime, then each simulation will take quite a long time. You need to draw a lot of random numbers, and that will, of course, delay it a lot. Now, in general, I would say that in the case studies we looked at, the actual expected number of transitions are quite low. And in that case, each simulation can go pretty quickly, but still you need to perform a lot of simulations to prove that, for example, something will not happen with a higher probability and 10 to the power of -6 or 10 to the power of -7. So yes, that can become a problem, definitely. And we are also, I should say, working on extending this numerical engine within the SMP tool.
But your numerical engine is based on symbolic math. Not numerical.
Yeah. So we have this simulation engine, which we have basically two engines. We have the numerical / symbolic engine. So it uses the MATLAB symbolic, but it has some numerical step within the end there.
Okay.
And we have the simulation engine, and the simulation engine has a wider range of what it can, what models it can handle at this particular moment.
Of course. Thank you.
Thank you.
My apologies. My internet, it had to happen today that my internet just got lost, and I connected via my cell internet, so it took me a little while to get it set up. I don't know if you had a chance to, there were any questions asked already. I don't see that in the channel, but I do have.
I answered one question live here, so while you were gone.
I'm sorry. I do
No
have
problem.
one more question for you. I don't know whether it was asked the same or not. Please, if it's already asked, just let me know. I was wondering if so. First of all, thank you very much for the presentation. Very great tool, and I think it's going to be very useful in the industry as well as for research purposes. My question is about the limitations of the tool. I'm also interested in implementation of simulation tools, and I have stayed away from MATLAB because it limits the scale for us. So how many states can be simulated simultaneously? As a follow-up, you had these OR states that then you can have you be in both states. Are there any limits on the number of OR states as well? So thank you.
I would say in general, there's no theoretical limit, but of course, if you are in, the more states you're in at the same time, you can assume that you have more transitions you need to sample, and that will increase the general, the general time it will take, of course. But there's no, we haven't seen any theoretical limit that says you can't have more than this, but of course, the greater the model in general, and that's mostly about the greater the number of expected transitions, the longer time it takes to perform the simulation.
Okay,
it
thank
was
you
a bit
very
connected
much.
to the other question, I got.
No, that makes sense, definitely. I would be curious to put it under stress and see what it will do. Yes. All right, thank you very much, Stefan. So let's welcome our third presenter, Adnan El Moussavi from Université Paris-Saclay and CNRS in France for the paper Sampling-Based Labor Propagation for Balanced Graph Partitioning. Adnan, please start when ready. You're muted, Adnan.
I'm trying to share my screen. Okay. So hello, everyone. I present for you today an experimental paper in which we have studied the impact of sampling on label propagation based partitioning algorithm for graph partitioning. So as you know, graph data is used more and more in many applications, as it allows us to have a better representation of data structure than other kind of data modeling like relational databases. In particular, it can be used to model relationship in social media, to model sales data, to model road networks, and many other kind of application and data types. The size of this kind of data, of graph data, is very massive, as we can see on the figure. And every day it increases. So to analyze such amount of data, we need to choose an efficient system. Mainly, we need to use parallel and distributed graph processing system in which we partition the graph on several machines. Then we can run some analysis task on the partitioned graph in order to have the results in a faster manner. But the graph is not a simple task. In fact, we have to take into account many constraints in order to have to get a good results. For example, to optimize the quality of partitioning, we need to take into account the balance of the partition, because when we partition the graph on several machines, if we have an unbalanced partitioning, it could lead to have a bigger load on some machines than others. So it could increase the processing time, and it could lead also to have bad results regarding to the quality. We need also, in the context of graph partitioning, to optimize other criteria like the edge cut, which means the number of edge that connecting the partition of the graph. Because if we have a high edge cuts, in fact, it will lead to have a high interconnection and network exchange between the different machines, and so it will increase computational time. So in order to have a good partitioning algorithm, we have to take into account these different constraints. In our paper, we have focused on label propagation-based partitioning, graph partitioning. And in particular, we have studied the impact of sampling on this kind of algorithm. We have based on a previous work that we have, in which we have defined a partitioning algorithm that allow us to take into account the balance constraint, either with respect to the number of edges in each partition or the number of vertices in each partition. So we have extended this algorithm and integrated to sampling-based heuristic in order to improve the propagation process in the partitioning algorithm. And then we have evaluated our algorithm and our heuristics using several experiments and several graphs in order to study the impact of the sampling on the quality and also on the computational time. So we have focused mainly on improving the initialization step of the graph sampling of the graph partitioning algorithm. Why the initialization? Because simply it has been proven in previous works and in several works that the initialization is a crucial step in any algorithm based on optimizing an objective function. In fact, the quality of initialization can dramatically impact the performance and the quality of the partitioning. And we have proved also in our previous work that a sample and a sample optimization and improvement of the initialization allowed us to have better quality and better computational time for the partitioning. So for this, we tried in this paper to study the impact of sampling and integrate the sampling in the initialization step by using a sample of the graph instead of taking the whole graph in the partitioning, and then propagate the result of the partitioning based on the sampling result. Why we use the sampling? Because the sampling allows us to have a smaller graph, so it allows us to reduce the computational time, and also generally sampling allows to preserve some characteristic of the graph, like subgraph and some embedded structure that we can find. So to study the impact of our algorithm, we have made several experiments in which we have studied the label propagation computational time, the stability of the quality regarding to the balance between the partition, and regarding also the quality of edge cuts. Regarding the time the computational time. Over all the graphs that we have used in our experiment, we have reduced the computational time with a gain that ranges between 6 and 40%. Regarding to the stability and the quality of edge cut, generally over all experiments, we get a stable quality. The quality of balance and edge gap was not reduced. We have also made some experiments to study the robustness to the parameter of the sampling and the algorithm. These experiments allowed us to discover some default value of the parameters that can be used and allow to the user to reduce the number of entries that he or she needs when he executing the algorithm. I don't know if I have more time, so I can show some of these results.
We are almost at time, so let's see if there are any questions already, and if there is more, you can continue with that. Or maybe you want 1 more minute, that's okay too, so your choice. Do you want to go for 1 minute?
I want to show this table that summarize our results. As you can see, this table presents the percent of gain of performance regarding to the quality. The MNU evaluation measure, it measures the balance between the partition. The edge cut measure the number of edge cuts between the partition, and the third one measure the gain of label propagation time. As you can see, in particular for the label propagation time, we have for a high reducing gain over all the graphs. Regarding to the edge cuts, it's almost stable. We have also some improvement on some graphs, and some few exception on 2 graphs regarding to the balance.
Thank you very much, Adnan. And so let's see if there are any questions from audience. I see none in the Slack channel. Please feel free to raise your hand or put your question in the Slack channel. I'll start with a question from myself. So in your presentation, you mentioned that there is an improvement between 6 and 40% that you have observed by applying this sampling-based propagation. Yes. I was wondering if there is any relation between the original structure of the graph and the level of improvement that you have seen, whether there is a relation between the sparseness or density of the graph, or basically the number of the complexity based on number of edges, or so on and so forth.
In fact, we use the sampling only for the initialization. So in the initialization step of the label propagation based partitioning, instead of using the whole graph to as an entry of the label propagation partitioning, we sample the graph and then we apply a first step of partitioning on the sampling graph. Then we propagate the results to other vertices, to the original graphs. So at the end of label propagation partitioning algorithm, we will have the whole graph. We will proceed the whole graph. So in our case, we still use the whole graph at the end of the algorithm. So I don't think we need to compare the state of the sampled graph to the state of the original graph. But we have tried.
Go ahead, please. Sorry, it seems that my connection is still not perfect. My apologies for that. Just a very quick follow-up question. So I was just wondering, so to clarify my question, what is this range of improvement based on? So, so you said that between 6 and 40%. What does it depend on?
It depends on the size of the graph. as we can see, in this table, the graphs are ordered in terms of the sizes, and you can see for the small graphs, we can see the large improvement, and for other kind of graphs with middle size and large size, we have less improvement. But for example, if I take a look to the Twitter graph, the 13% of label propagation time, in fact, it's correspond to many hundreds of seconds.
Great, thank you very much. Thank you very much for your presentation and for thank all the presenters in this session. Once more time, my apologies for my internet connection issues. It must happen today of all days. I say goodbye and hand over to Philip for the closing session.
Thank you so much.
Thank you. Bye.
Let me share my screen and then we can get started with the closing. So, all good things need to come to an end, and so does this ICPE, I guess. So the only thing, we only have 2 more matters on the agenda for today and for this conference. So of course, the first thing is that we as kind of the conference organizers really need to thank everybody who was involved with the conference. And we know that the virtual conferences are not always easy. I know that they need a lot of commitment from everybody involved, but really a big heartfelt thanks from the entire organizing team to everybody who was involved in the conference, including, of course, the authors, the people who present here over Zoom, which can be a bit awkward, I know, all the session chairs, everybody who reviewed papers, and of course, all the people who attended the conference, either through live stream or by watching the videos or both. So many thanks from everybody who was involved in the organization, me, Nico, Steffen, Tanfeng, Arthur, everybody. Thank you all for helping us out and making this very good iteration of ICPE again, I feel. I should say, you know, you have heard a lot from me and from a couple of other co-organizers over this week, but there were a bunch of other people who helped us a lot in the organization of this conference. I'm not going to name them all, but you know, everybody who has organized the conference at some point knows that there are a lot of small things that you kind of need help with, including managing the website, organizing the award session, organizing the tutorials, arranging that proceedings get made, and so on. So there were a lot of people in roles that might not be quite so visible that had a lot to do with making this ICPE a success this year. And I think we want to thank all of them to make our lives a lot easier than they would have been otherwise if we would have had to do everything ourselves. So thanks everybody. And this is pretty much everything we want to say about ICPE 2022. So now the last thing on the agenda really is to hand over to the next year's ICPE chairs. And I think they are in the call, right? And I think we have a small presentation about the next ICPE, which, fingers crossed, should be physical again. So I'm gonna stop sharing and then stop sharing. That's what I wanted to do. And then Marco, I think you did have a presentation plan, right?
I do. I have a small presentation. I hope you can see my slides.
Yes.
Okay, so good. So first of all, congratulations for this organization this year. I know that it is not easy to organize these online conferences. I've done it in the past, and this is really a challenge, and I think it was very successful. So I hope next year we manage to all get together in Coimbra, Portugal. I'm going to very briefly introduce the conference and Coimbra and so on. So welcome to Coimbra. I hope I can welcome you to Coimbra next year. I think I had a problem with my slides. Can you see the slide?
Very efficient presentation.
Started by the end, right? Okay, so first of all, when it will be, these are tentative dates. We are still discussing the dates among the organizers and the steering committee, but in principle, it will be between April 15, which is a Saturday, and April 19. This is kind of 2 weeks after Easter. I think Easter is on the 9th, so 1 week after Easter. But as I mentioned, this is yet to be confirmed, but most probably these will be the dates. Where it will be in Coimbra, of course, Coimbra in Portugal, a small city in the center of Portugal. The organizers, the team, for the time being, we already know some of the names. So as co-chair, general co-chairs, it will be myself from the University of Coimbra and Valeria Carderini from the University of Rome, Tor Vergata. Then as research track co-chairs, it will be Antinisca Di Marco from L'Aquila University and Petro Tuma from Charles University. As industry chair, it will be David Davy from MongoDB. And as local arrangement chair, it will be my colleague Nuno Antunes, also from the University of Coimbra. Of course, the team is not complete yet. The other names for other positions will be disclosed very soon. Just a second. So where this will be? So this will be in Portugal. For sure, most of you know where Portugal is, in the very western side of Europe. It will be in Coimbra. So Coimbra is this small place in the center of Portugal. So it is kind of 200 kilometers to the north of Lisbon and 100 kilometers to the south of Porto, which are the main cities in Portugal. Coimbra is very well known from university. In fact, the University of Coimbra is one of the oldest universities in Portugal. What you see here in this photo on the top of the hill is the old campus, or the oldest campus of the University of Coimbra, which will be probably the place where we are going to organize the conference. There is a lot of tradition in Coimbra. Coimbra is an old city. It was the capital of Portugal many centuries ago. What you see here is the main campus of the university. So this is the rector, where the rector stays, so the administrative services and so on. This used to be a palace from the king, and we will have the opportunity to meet all these places. This is a very old library. Okay, beautiful place. Also one of the most beautiful libraries in the world. We have books from the 15th century stored here, and it can be visited. It is done. This is really gold. It's not just golden paint. Most of it's gold that the Portuguese brought from Brazil many centuries ago. So there is still a fight about this that we need to arrange. Also, there is a huge tradition among students. So we have a lot of protocols and so on. It will be nice for you to see what is going on. But Coimbra is not only about university. It is also a technological city. In fact, now we have some of the biggest tech companies in Portugal. These are just some examples. Fitsai, it's a unicorn company. It is at this point valued in more than $1 billion. It has been created by a colleague of mine, of 3 colleagues of mine from the University of Coimbra. Critical Software is another company that is still based in Coimbra. They developed software for critical systems. With software, they developed software for mobile devices. And TalkDesk, although it was not created in Coimbra, it is another unicorn. It was not created in Coimbra, but they have a huge laboratory in Coimbra because it's a place where they can find work power, manpower. So they are based there. So these companies are very well known. They are starting to show everywhere. And it is a fact that major companies are moving to Portugal, and some of these major companies are moving to Coimbra, and I hope I can somehow bring these companies also to the conference. Okay, to have some presence from these companies in this conference, because this would be very good. Regarding the possible venues, we don't have a decision yet where the conference will take place. It will be in Coimbra. I have a few options. It can be hosted at university, of course. It can be organized also inside the Science Museum in Coimbra, Convento de São Francisco, which is an old monastery, and also in some hotels. I'm still assessing what is the best option here. There are advantages and disadvantages in different options, but very soon I hope I can announce what is the best place for doing it. So these pictures here just show some of the places where we can organize the conference. The one in the top left is the monastery. So we could be inside the old church. Let's see if this is a possible one. The one the top right is Quinta das Lágrimas, is an old hotel. In the bottom left side, it's my department. Okay, it's new. It's not so interesting as the other ones. And on the right side in the bottom, it is the Science Museum. So I hope very soon I can announce what is the place to organize the conference. So how to reach Coimbra? It's quite easy to reach Coimbra. So you can fly from almost any capital in Europe, from several places also in South America, and also from several places in the United States, and or North America, also including Canada. And also from some places in Africa. But from Europe is very easy to reach. You can fly either to Lisbon or Porto, and then take a fast train to Coimbra. So once you reach Lisbon, you take a couple of hours to get to Coimbra. If you go through Porto, you take a little bit more than 1 hour to get to Coimbra in a fast train. So it's quite easy to reach. These are, in this map, you see only TAP flights. So there are many more flights than the ones that are shown here by other companies that also fly to Lisbon and Porto. So just to convince you to come to Coimbra, so Portugal is very well known as a topic touristic destination. There are great cities to visit: Porto, Lisbon, Braga, Évora, and so on. So if you come to Portugal, you should consider staying a few more days to visit other places. There are plenty of UNESCO World Heritage sites. This includes downtown Coimbra and University. It has been classified as a UNESCO site. There is fantastic food and fantastic wine, and I promise you that you have fantastic food and fantastic wines at the conference. I promise this. And also Portugal is a quite affordable country, as you know. Okay. Besides this, is one of the safest countries in the world. It has been classified as the third most safe country in the world, regardless of what these classifications means. It is very safe. About the research track, I would pass the word to I think that Antoniska is online. Antoniska, are you there?
Yeah, I'm here. Marco, thanks a lot. I think that my slide is this slide before, this one, because this is industry and experience track, no? Yes. Yeah, okay. Thanks a lot. Thanks. I'm very happy to join the organizing committee, and in Portugal that I love. And I trust you for I know that in Portugal you can have good wine first and then good food. About the research track, we have a tentative deadline for the submission that is mid of October. And of course, we will have all ICPE, ICPE favorite topics that refer to performance measurement, monitor analysis, modeling, and so on and so forth. But we are looking for new topics. So please, in case you have any idea email me and Peter. We, of course, we will be happy to have evaluation artifact as well. So for any suggestion, if you have any idea, please email us. And thank you to Peter, that will be my colleague in the program chair service. Thanks a lot.
Okay, thank you, Antoniska. So moving to the industry, David, you are online also, right?
Yes. So we'll be aligned with the research track, and as been mentioned several times this week, ICPE has been a great place for encouraging interaction between practical experience and theory, and we hope to continue that. Well, we will continue that next year. So trying to encourage inclusion of industrial experience and practical challenges. And Marco will definitely have to see about getting some submissions from the local companies and getting them involved. And just in general, trying to make sure that we share, implementations and evaluations and data so that everyone can learn about what the practical problems are and build on those. So looking forward to great submissions and a great program next year. And definitely, I'm going to be in Portugal one way or the other. If for some reason we're virtual again, you need to find me a desk there because I'm coming.
For sure, it will be a pleasure. Okay, so I think thank you, David. This concludes our short presentation. This is just a teasing for you to consider coming to Coimbra. Hopefully it will be a face-to-face event. I believe it will be a face-to-face event. So if you have any questions, any comments, please go ahead.
So on behalf of the steering committee, I want to thank you, Marco, for taking this important role. You said you believe it will be physical, right? Well, asking people to organize conferences for the next year, oftentimes people were saying to me, we believe it will work, but we want to see first, right? After several years of believing, they were saying, I will do a conference, but I want to see one successful physical take place, and I do it the year after that, right? Although I'm convinced it will work, we believe, we have faith, but let me see first it works next year, and then I will do the year after, right? So I do realize, that, you're also taking a risk here, although it's a low risk, and we all would agree chances are very high that this time it will work. But nonetheless, you're taking a risk, and I want to thank you for taking this risk and for being ready to serve the community by organizing the first, hopefully, physical conference after this pause we have. And also, of course, the rest of the committee that was presented, that we very much look forward to it. But before this, and I want to say also on behalf of the steering committee, to give a big thanks to the organizers of this year's conference. Philip was thanking the organization team. I want to thank the main people involved, and especially two people, Nicholas and Philip, the PC chairs, stood out to do a really extraordinary amount of work. I was speaking to Nicholas occasionally, and he told me that he had, I don't know how many thousands of emails. I don't remember, was it 3,000? Was it something more?
Yeah, it's only 3,000 in the email box, but we have tons more in GitLab and Slack.
Yeah, so just this number gives you an impression of the complexity and the amount of work involved in this event. And we are aware of this, and we want to thank you for your service here. And also we are aware that you did not only your own job, but beyond your own job for many reasons. And you were actually serving us more than just PC chairs. And we have seen this, and we are not taking it for granted. And finally, I think it was very well organized, everything went very, very well. And I want to say also that it's not easy to organize such a conference, especially given that it's not the first virtual conference, it's not even the second, but it's the third virtual conference. So if it is challenging to organize a first one, it is even more a second and even more a third, because we have seen that as we have these events, somehow it gets more difficult to keep people on board, to have them listen. So in a way, there is some tiredness in the community for virtual conferences. We are all aware of this, and not only at ICPE. And despite of this, you did excellent job in running this conference, and everything went very well. I'm very excited about the result, and thank you very much. And also, of course, to the rest of the team for serving. And maybe Vittorio, you want to add something to this? The co-chair of the steering committee?
No, Samuel, I think you have said everything. Just thanks to all organizing committee this year. And I told you the same thing last year, but I hope really next year not to see any avatar anymore on my screen, but to see real people in a real room with this exciting location. This is the best wish that we can give to ourselves. So I don't want to speak more. We said the same thing last year, but really yes. Next year will be the one. And we start again for physical conferences that personally I need so much. So, and okay, good things to everybody.
Thank you very much. And we look forward to seeing everyone in Coimbra.
Thank you so much. See you in Portugal.
See you in Portugal.
See you in Portugal.
Bye-bye, guys. Thank you.
Bye-bye.
Bye-bye. Great job. Looking forward to next year.
Very great job.